the last journey you'll ever take. Close your eyes and imagine the most profound journey possible. Not to another country, not to another planet, but to a place where the very fabric of reality tears apart, where time stops being time and space stops being space, where everything you thought you understood about the universe, about existence itself, dissolves into something so strange that our most brilliant minds can barely describe it, let alone truly comprehend it. You're about to fall into a black hole. This is not a metaphor. This is not hyperbole. We're going to walk through, moment by moment, sensation by sensation. What would actually happen if you found yourself falling toward one of the universe's most mysterious and terrifying objects? We'll experience it together. The approach, the acceleration, the strange distortions of light and time, the crossing of the event horizon, and finally the journey to the singularity at the center, where all our physics breaks down and reality itself comes to an end. But before we take this journey, before we commit to the fall, you need to understand what we're dealing with. A black hole is not a hole. It's not an opening or a tunnel or a portal, despite what science fiction might suggest. It's a region of space where gravity has become so overwhelmingly powerful that it creates a one-way membrane in space-time. Cross that membrane, called the event horizon, and you can never come back. Not because you lack a powerful enough rocket, not because the journey would take too long, but because back ceases to be a direction you can move in. The singularity becomes your future as inevitably as tomorrow, and there is no path through space-time that leads anywhere else. Think about that for a moment. We're used to thinking of the future as uncertain, as a space of possibilities. You might go to the store tomorrow, or you might stay home. You might call a friend or read a book or do nothing at all. The future is open. But inside a black hole's event horizon, there is only one possible future, the singularity. Every path through space-time, every possible action you could take, every conceivable trajectory leads to the same place. The singularity is not a location you might visit, it's your destiny, written into the geometry of space-time itself. Why this journey matters. You might reasonably ask, why should I care about something that will never happen to me? The odds of any human falling into a black hole are so astronomically small that they're essentially zero. You're far more likely to be struck by lightning while winning the lottery during a meteor impact. Black holes, despite their terrifying power, occupy such tiny fractions of space that they're effectively impossible to encounter accidentally. Yet this journey matters profoundly for several reasons. First, because black holes represent the most extreme conditions the universe can produce. By understanding what happens at these extremes, we understand the limits of physics, the boundaries where our theories work and where they spectacularly fail. Black holes are laboratories for testing our deepest ideas about reality, about space, time, gravity, quantum mechanics, information, causality. Every strange phenomenon we'll encounter during our fall teaches us something fundamental about how the universe works. Second, because confronting the extreme makes us appreciate the normal. We live in a gentle universe, cosmically speaking. The curvature of space-time on Earth is so slight that we can live our entire lives without noticing it. Time flows at a steady rate. Space extends in 3 dimensions we can move through freely. Cause precedes effect in orderly fashion. All of this is special, contingent, and worth marvelling at. By seeing how bizarre reality becomes near a black hole, we gain deeper appreciation for the stable reality we inhabit. Third, because imagination and thought experiments have a noble history in physics. Einstein himself developed his revolutionary theories by imagining impossible scenarios, riding alongside light beams, standing in accelerating elevators, watching clocks in motion. These thought experiments led to insights that mathematics alone might not have provided. By imagining our fall into a black hole, by making it visceral and personal, we can understand truths about space-time that equations, however elegant, might obscure. Finally, because this journey confronts us with the ultimate mystery. At the center of every black hole lies the singularity, a point or perhaps a ring where density becomes infinite, where space-time curvature becomes infinite, where all our physics breaks down. The singularity is hidden behind the event horizon, forever inaccessible to observers outside, protected by what we call cosmic censorship. But you, falling inward, will encounter it. And we don't know what happens there. Our best theories stop working. The singularity might be a place where quantum gravity, a theory we don't yet have, finally becomes necessary. Or it might be something else entirely, something we can't even conceive of with our current understanding. The black hole. We're falling into. For our journey, we'll approach Sagittarius A, the supermassive black hole at the centre of our Milky Way galaxy. It's a monster, containing about 4 million times the mass of our Sun, yet compressed into a region roughly the size of Mercury's orbit. Its event horizon, the point of no return, stretches approximately 12 million kilometres across, about 8 times the distance from Earth to the Sun. Why choose a supermassive black hole rather than a smaller, stellar mass black hole formed from a collapsed star? Because the experience will be less immediately violent. The key factor determining how quickly tidal forces, differences in gravitational pull across your body, will tear you apart is not the absolute gravity, but the gradient of gravity, how quickly it changes over distance. For a supermassive black hole, this gradient is much gentler. You'll be able to cross the event horizon intact, even comfortable, still able to observe and experience what's happening. With a stellar mass black hole, you'd be shredded by tidal forces long before reaching the horizon, torn atom from atom in a process physicists call spaghettification. That's a less interesting journey, cognitively speaking. Sagittarius A is real, approximately 26,000 light-years from Earth, hidden behind clouds of dust and gas that obscure it in visible light, but revealed through radio waves and X-rays. Radio telescopes have mapped the orbits of stars near it, stars moving at thousands of kilometers per second in tight orbits that betray the presence of an enormous invisible mass. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A's shadow, the dark silhouette created by the event horizon against the glowing material surrounding it. This is not a theoretical object. This is a real monster in our cosmic backyard, and we're about to fall into it. What you'll experience. As we fall, you'll experience phenomena that defy everyday intuition. Time will behave strangely, running at different rates depending on where you are and where observers watching you are positioned. Light from the universe behind you will shift and distort in ways that seem impossible. The black hole itself will create a vast darkness in your vision, a perfect circle of absolute black surrounded by distorted starlight. Gravity will pull on you more strongly at your feet than at your head, creating tidal forces that stretch you. Initially, this stretching will be gentle, barely noticeable, but as you fall deeper, it will intensify exponentially, eventually reaching levels that no human body could survive. But we'll cross that bridge when we come to it, literally. For now, in the early stages of the fall, you're intact and conscious. You'll cross the event horizon, possibly without even noticing the moment it happens. There's no physical surface there, no barrier or membrane you can touch. It's simply a boundary in space-time, a point of no return defined mathematically. From your perspective, the crossing might be smooth and unremarkable. But from the perspective of someone watching from outside, they'll see something very different, something that seems to violate causality and common sense. Inside the horizon, the rules change fundamentally. The radial direction, what we normally think of as inward toward the centre, becomes a time direction. You're not moving toward the singularity in space, you're moving toward it in time. It's as inevitable as tomorrow, as inescapable as next Tuesday. And unlike the future you're used to, which is uncertain and probabilistic, this future is absolutely determined. The singularity is not a place you might reach, it's a time you will reach. And at the singularity itself? We don't know. Our physics fails. Our equations produce infinities, infinite density, infinite curvature, infinite tidal forces. These infinities are our theory's way of saying, I don't know what happens here. The singularity might be the end of space-time, the final frontier where reality stops. Or it might be something else, something quantum mechanics or string theory or some future theory might explain. Or it might be a doorway to something we can't even imagine. The path ahead. Our journey will unfold in stages, each more strange than the last. We'll begin far from the black hole, watching it slowly grow in our field of view as we fall faster and faster. We'll examine the distortions of light, the warping of space, the slowing of time. We'll approach the event horizon and carefully consider what it means, both from our perspective and from the perspective of those outside. We'll cross that ultimate boundary and explore the bizarre interior where time and space have exchanged roles, where the future is a place rather than a duration. We'll confront the singularity and contemplate what might happen there, not just to our bodies but to information itself, to causality, to the nature of existence. We'll step back from the personal experience and consider the bigger questions. What do black holes tell us about the nature of reality? How do they challenge our understanding of physics? What mysteries remain unsolved? What might lie beyond our current knowledge? And finally, we'll consider what it all means, not just for physics and cosmology, but for human understanding, for our place in the universe, for the limits of knowledge itself. A note on perspective. Throughout this journey, we'll shift between different perspectives. Sometimes we'll experience the fall from your point of view. What you see, what you feel, what you understand is happening to you. Sometimes we'll step outside and consider what distant observers see, what the mathematics describes, what the physics predicts. These perspectives sometimes seem to contradict each other, and that's not an error but a feature of relativity. There is no universal now, no God's eye view that reconciles all perspectives. Reality itself depends on where you are and how you're moving. This can be disorienting, but it's essential. One of the most profound lessons of relativity is that reality is not absolute but relational. What happens now from one perspective might be in the past or future from another. Events that are simultaneous for one observer are not simultaneous for another. The order of events can change depending on your motion. And nowhere is this more dramatic than near a black hole, where the curvature of space-time creates such extreme relativistic effects that different observers experience fundamentally different realities. So as we journey together, remember, we're experiencing multiple realities simultaneously, each valid from its own perspective, each describing the same events, but in incompatible ways. This is not confusion, but insight into the nature of space-time itself. Preparation for departure. Take a deep breath. Check that you're comfortable, wherever you're experiencing this from. What we're about to do requires imagination and courage. Not physical courage, since we're not actually in danger, but intellectual courage to confront ideas that violate intuition, that challenge everything you thought you knew about space and time. The black hole awaits. Sagittarius A, with its 4 million solar masses compressed into a region the size of a planetary orbit, pulls at us with gravity so intense it bends light, stops time, and eventually tears apart the fabric of space-time itself. We're going to fall into it, to experience firsthand what happens when you approach the most extreme environment the universe can create. This is not a journey anyone would take willingly, but through the power of physics and imagination combined, we can visit this cosmic abyss and return to tell the tale, or at least to understand why no tale could ever really be told by someone who made the journey for real. The event horizon beckons. The singularity awaits, hidden behind that one-way membrane, patient and inevitable. Let us begin our fall into darkness, into mystery, into the heart of one of the universe's deepest secrets. The cosmos is about to teach us what happens when reality breaks. First glimpse. The approach begins, distance 100,000 kilometers. You float in the void, and for the first time you can really see it. The black hole, Sagittarius A, the monster at the heart of our galaxy. Except see isn't quite the right word, because a black hole is by definition invisible. It emits no light. It reflects no light. It is a region of absolute darkness, a wound in the visible universe. Yet somehow, paradoxically, it's one of the most spectacular sights imaginable. What you see is absence defined by presence. At the center of your field of view is a perfect circle of darkness, blacker than anything you've ever encountered. Not the black of a closed room or a moonless night. Those blacks still contain scattered photons, still have texture and variation. This is absolute black, a void so complete that your brain struggles to process it. It's like looking at a hole in reality itself. The darkness is surrounded by chaos. The familiar constellations you've known all your life are twisted beyond recognition. Stars that should be behind the black hole appear beside it, above it, their light bent around the gravitational well in paths that seem impossible. Some stars appear as multiple images, their light taking different routes around the hole, arriving at your eyes from different directions. The effect is nauseating, disorienting, like looking at the universe through a cosmic funhouse mirror. This distortion is gravitational lensing, the bending of light by intense gravity. You've seen examples before, distant galaxies lensed by clusters of galaxies between them and us, creating arcs and rings of distorted light. But this is different. This is immediate, surrounding you, impossible to escape. Every direction you look, the universe is warped. The shadow itself, that circle of perfect darkness, is larger than the event horizon, the actual point of no return. The shadow has a radius about 2.5 times larger than the horizon radius. This is because there's a region around the hole where light can orbit, circular or spiraling paths that neither escape nor fall in immediately. This photon sphere sits outside the event horizon, and it's the boundary of the shadow you see. Light rays that pass inside this sphere inevitably spiral in and are lost. Light rays outside can escape, though heavily bent. The boundary between them creates the shadow's edge. As you stare at this shadow, you notice something else, something spectacular. If the black hole is feeding, if it's pulling in gas and dust from its surroundings, that material forms an accretion disk, a vast spiral of matter rotating around the hole before its final plunge. The disk glows with incredible intensity, heated to millions of degrees by friction as material rubs together in its death spiral. But the disk doesn't look normal. Nothing near a black hole looks normal. The side of the disk rotating toward you blazes brighter than the side rotating away. This is relativistic beaming. When something moves near light speed, it emits more radiation in its direction of motion. The material in the inner accretion disk is moving at significant fractions of light speed, so the approaching side dramatically outshines the receding side. More strangely, you can see both the top and bottom of the disk simultaneously. Light from the part of the disk behind the black hole curves up and over, bent by the intense gravity, reaching your eyes from above the hole. You're seeing views that should be impossible, perspectives that violate every intuition you have about how light travels. But near a black hole, light doesn't travel in straight lines. There are no straight lines. Space-time itself is curved, and light follows that curvature. You check your instruments, assuming you still have functioning instruments after whatever disaster brought you to this predicament. The readouts are bizarre. Spectral lines from the accretion disk are shifted, compressed to higher frequencies on one side, stretched to lower frequencies on the other. This is the Doppler shift, the same effect that makes an ambulance siren change pitch as it passes you. But there's an additional shift, a gravitational redshift, caused by light climbing out of the deep gravitational well. Photons lose energy escaping the intense gravity, their wavelengths stretching toward red. The temperature readouts make no sense. The material in the inner disk is millions of degrees, hot enough to emit X-rays and gamma rays. Yet the radiation reaching you is shifted to lower energies, cooled by the gravitational redshift. The black hole's gravity drains energy from everything trying to escape it, even light. You notice your motion is accelerating. You're falling, pulled by gravity so intense it defies comprehension. Currently you're falling at thousands of kilometers per second and accelerating steadily. In the reference frame of a distant stationary observer, you're approaching relativistic speeds, though you don't feel anything unusual. From your own perspective, you're in free fall, which means you feel weightless, just like an astronaut in orbit. But this isn't orbit. You have no tangential velocity to balance the gravitational pull. You're falling straight in, or as straight as straight means in this warped geometry. Your trajectory is what's called a geodesic, the closest thing to a straight line in curved space-time. From your perspective, you're simply moving forward, following an inertial path, but the curvature of space-time bends that path inward, toward the singularity. You're not being pulled or pushed in any conventional sense. Rather, the shape of space-time itself is directing you. Time is already behaving strangely, though you don't feel it personally. Your heartbeat, your breathing, your thoughts, everything proceeds normally from your perspective. But if you could somehow compare your watch to a watch held by someone far from the black hole, hovering safely at a great distance, you'd see discrepancies. Your watch runs slower. For every hour that passes for you, more than an hour passes for the distant observer. This time, dilation is not an illusion or trick of perception. It's fundamental to how space-time works near massive objects. The closer you are to a source of gravity, the slower time passes relative to regions farther away. This has been measured on Earth. Atomic clocks at sea level run measurably slower than identical clocks on mountains. The difference is tiny, but it's real, and it accumulates. GPS satellites must account for this time dilation or they'd quickly lose accuracy. Near a black hole, the effect becomes extreme. Time doesn't just slow slightly, it slows dramatically, and the effect intensifies as you fall closer. This time dilation will eventually create a bizarre disconnect between your experience and what external observers see. They will watch you approach the event horizon, slowing down, your image growing dimmer and more redshifted, never quite reaching the boundary. From their perspective, you never fall in. You're frozen at the edge of forever, but from your perspective, something entirely different happens. You will reach the horizon in finite time, your time, and you will cross it, and you will continue falling. Both perspectives are real. Both are valid descriptions of the same events, but they're so different, so seemingly contradictory, that reconciling them requires abandoning the idea of a universal now. There is no cosmic clock, no God's eye view where everything happens in synchronized sequence. Reality itself is relative, dependent on motion and position. You think about what lies ahead. The event horizon, still thousands of kilometers away but approaching rapidly, marks the boundary of the region from which no escape is possible. It's defined by the condition that the escape velocity equals the speed of light. Outside the horizon, a powerful enough rocket could escape. Inside, not even light can escape, which means nothing can, since nothing travels faster than light. But the horizon is not a physical surface, it's not made of anything. It's simply a boundary in space-time, a point of no return defined mathematically. Will you notice when you cross it? Will there be some sensation, some indication that you've passed through the one-way membrane? Or will it be smooth and unremarkable, like crossing an arbitrary line on a map? You also think about what observers outside will experience. You know they'll never actually see you cross. They'll see you approach asymptotically, your image fading, redshifting, slowing, but never disappearing completely. Long after you've crossed and continued to the singularity, long after you've ceased to exist in any meaningful sense, your image will still be visible hovering just outside the horizon, frozen in time. This image will persist for millions or billions of years, gradually dimming, gradually redshifting to longer and longer wavelengths, but never quite vanishing. This seems paradoxical. How can you cross the horizon from your perspective, while never crossing it from an external perspective? The resolution lies in understanding that space-time near the horizon is so dramatically curved that the very concept of simultaneous breaks down. What happens now at the horizon from an external viewpoint simply doesn't map onto what happens now from your viewpoint. The events are not synchronized. They can't be synchronized. Simultaneity is not absolute but relative, and near a black hole, this relativity becomes extreme. As you fall closer, the shadow expands, filling more and more of your visual field. The distortions intensify. Stars that were recognizable constellations are now unidentifiable smears of light, their positions shifted by the warped geometry. The accretion disk, if present, glows with hellish intensity, matter screaming its last moments before the plunge. You notice temperature changes. Paradoxically, you're getting colder, not warmer. Despite approaching this incredibly energetic environment, despite the million-degree accretion disk nearby, you're cooling. This is because you're falling so fast that the radiation from the disk is heavily blue-shifted in front of you but red-shifted behind you. The net effect, depending on your trajectory, might actually reduce the energy you absorb. You also notice the beginning of tidal forces. These are differences in gravitational pull across extended objects. Your feet, closer to the black hole, feel slightly stronger gravity than your head. At this distance, the effect is minimal, perhaps producing a sensation like hanging upside down, a gentle pull that's noticeable but not painful. But this is just the beginning. Tidal forces grow exponentially as you fall closer, and eventually they'll become violent beyond description. The Roche limit, the distance at which tidal forces overcome structural strength, is still far below you. Human bodies are remarkably sturdy in some ways, held together by molecular bonds that can resist substantial force, but those bonds have limits, and you're approaching a place where gravity will exceed those limits, where the difference in gravitational pull between your head and feet will become so large that no material, No structure, no organization of matter can resist it. But that's in the future. For now, you're intact, conscious, still able to observe and think and experience what's happening. The black hole grows in your vision, the shadow expanding, the distortions intensifying. You fall faster, accelerating toward the speed of light. Though you'll never quite reach it from an external observer's perspective, you're committed now. There's no turning back, not that there was ever really a chance to turn back. The gravitational binding energy is simply too large. You would need to accelerate at impossible levels to escape, would need a rocket more powerful than anything physics allows. So you fall, and you watch, and you try to comprehend what's happening to you. The universe you're leaving behind, the universe of stars and planets, of normal space and time, of cause and effect proceeding in orderly fashion, still surrounds you. But ahead lies something fundamentally different, a realm where the rules change in ways that mathematics can describe, but human intuition cannot fully grasp. The shadow grows, the stars distort, and your acceleration continues, inexorable as gravity itself, pulling you toward wonders and terrors beyond imagination. The journey has truly begun. The nature of darkness. What are you falling into? Before we continue your fall, before the situation becomes too extreme for reflection, we need to understand what exactly a black hole is, not just as an abstract concept, not just as equations on paper, but as a physical reality you're now experiencing firsthand. Understanding the monster makes the journey more meaningful, and frankly, you have time. From your reference frame, subjective time measured by your thoughts and heartbeat, you have hours or days before reaching the event horizon, depending on the black hole's size and your starting distance. A black hole is not a hole. That's the first misconception to discard. It's not a tunnel through space, not a portal to another dimension, not an opening or cavity or void. It's a region, a volume of space-time where gravity has become so overwhelming that it creates a one-way membrane. Cross that membrane and you cannot return. Not because the journey back would be difficult or expensive or dangerous, but because back ceases to be a direction that exists. All paths through space-time lead forward, toward the singularity. Think of it this way. Right now, in normal space, you can move in any of three spatial dimensions. Forward and back, left and right, up and down. You have freedom of movement. But you have no freedom in time. You move into the future at a steady rate, 1 second per second, and you cannot move backward. The past is inaccessible. Not because you lack a time machine, but because the structure of causality forbids it. Inside a black hole's event horizon, something similar happens to space. The radial direction, the direction toward the singularity, becomes time-like rather than space-like. You move toward the singularity at a steady rate, just as you normally move through time, and you cannot move backward. The singularity is not a place you might reach, it's a time you will reach. It's in your future as inevitably as next Tuesday. This transformation of space into time, this conversion of a direction you normally have freedom to move in into a direction you're forced to move in, is one of the most profound and counterintuitive aspects of black hole physics. It's not a metaphor, it's literal. The mathematics describing the space-time geometry inside the horizon shows clearly that the radial coordinate becomes time-like. Moving toward the singularity is not a spatial journey, but a temporal one. Black holes form through gravitational collapse. In normal circumstances, matter maintains its size through various pressure mechanisms. Ordinary objects like rocks resist compression through electromagnetic forces between atoms. Stars resist gravitational collapse through thermal pressure generated by fusion reactions in their cores. When massive stars exhaust their fusion fuel, thermal pressure drops catastrophically. Gravity suddenly has no opposition. For stars with cores below a certain mass limit, about 1.5 times the Sun's mass, electron degeneracy pressure can halt the collapse, creating a white dwarf. This is a quantum mechanical effect arising from the Pauli exclusion principle, which forbids identical particles from occupying the same quantum state. Electrons resist being compressed beyond a certain point simply because there's no room for them in quantum state space. For more massive cores, electron degeneracy pressure fails. The collapse continues, crushing electrons and protons together to form neutrons. Neutron degeneracy pressure can then halt the collapse, creating a neutron star, an object with the mass of the Sun compressed into a sphere just 20 kilometers across, where a teaspoon of matter weighs as much as Mount Everest. But even neutron degeneracy pressure has limits. For cores exceeding about 3 solar masses, the exact limit depends on poorly understood nuclear physics. No known force or pressure can resist gravity. The collapse continues beyond the neutron star stage. The matter compresses to infinite density, creating a singularity, and an event horizon forms around it. A black hole is born. This collapse happens fast, milliseconds from the moment thermal pressure fails to the formation of the event horizon. The energy released is staggering, typically manifesting as a supernova that briefly outshines an entire galaxy. The outer layers of the star are blasted into space at significant fractions of light speed. The core collapses into darkness, but not all black holes form this way. The supermassive black hole you're falling into, Sagittarius A, with its 4 million solar masses, couldn't have formed from a single stellar collapse. Such massive stars would be unstable, tearing themselves apart through radiation pressure long before they could collapse. Supermassive black holes probably formed through different mechanisms, direct collapse of massive gas clouds in the early universe, or gradual growth through accretion and mergers of smaller black holes over billions of years. The details of formation vary, but the end result is always the same: a region of space-time from which nothing can escape, defined by an event horizon, a boundary that light itself cannot cross. This horizon is not a physical surface, but a null surface in space-time geometry, a place where certain light-like paths remain at constant radius rather than escaping or falling in. The event horizon's size depends only on the black hole's mass. For a non-rotating black hole, the radius is simply proportional to mass, double the radius. Sagittarius A, with 4 million solar masses, has a horizon radius of about 12 million kilometers. A stellar mass black hole with 10 solar masses has a radius of just 30 kilometers. The density inside the horizon can actually be quite low for supermassive black holes. If you could measure density at the horizon, and you can't for reasons we'll explore, it would be less than the density of water for the largest black holes. This seems paradoxical. How can something with lower density than water be impossible to escape from? The answer is that what matters is not density but total mass enclosed within the horizon, combined with the curvature of spacetime that mass creates. It's the geometry that traps you, not the density of what's inside. Most real black holes rotate, sometimes at significant fractions of the maximum possible rotation rate. A rotating black hole, described by the Kerr solution rather than the simpler Schwarzschild solution for non-rotating holes, has more complex structure. It has 2 event horizons and an ergosphere, a region outside the outer horizon where spacetime itself is dragged along with the black hole's rotation so strongly that nothing can remain stationary. Stand still in the ergosphere and you'd be dragged around the black hole whether you like it or not. The singularity in a rotating black hole is not a point but a ring, a circle of infinite density and curvature. The mathematics suggests that paths exist passing through the center of this ring without encountering the singularity itself, potentially emerging into other regions of spacetime, other universes, other times. But whether these mathematical possibilities correspond to physical realities remains unknown and probably unknowable. The singularity is hidden behind the horizon, protected by what we call cosmic censorship. We cannot observe it directly, cannot send probes to report back, cannot verify what actually happens there. What we do know is that black holes are characterized by remarkably few properties. There's a theorem, the no-hair theorem, stating that black holes are completely described by just 3 numbers: mass, electric charge, and angular momentum, rotation. Everything else, every detail about the matter that formed the whole, whether it was made of protons or antiprotons, of stars or gas clouds, of normal matter or something exotic, is lost. 2 black holes with identical mass, charge, and rotation are absolutely indistinguishable, regardless of their formation history. This leads to profound questions about information. In quantum mechanics, information is sacred, it cannot be destroyed, only transformed or hidden. The state of a system at one time determines its state at all future times. But if all the information about what falls into a black hole is lost, isn't this principle violated? This is the black hole information paradox, one of the deepest puzzles in theoretical physics. Stephen Hawking, working in the 1970s, made the paradox worse by showing that black holes emit radiation through quantum effects near the horizon. This Hawking radiation carries energy away from the black hole. which must therefore lose mass to conserve energy. Over extremely long timescales, far longer than the current age of the universe for stellar mass or supermassive black holes, this radiation causes the black hole to evaporate completely. But Hawking radiation appears to be perfectly thermal, carrying no information about what fell in. If the black hole evaporates completely and the radiation is thermal, then all information about what fell in is permanently lost in apparent violation of quantum mechanics. Reconciling this paradox has occupied theoretical physicists for decades and led to revolutionary ideas like the holographic principle, the notion that all information in a volume of space might be encoded on its boundary, like a hologram. The resolution might involve quantum entanglement between particles inside and outside the horizon, or subtle correlations in Hawking radiation that preserve information in ways not initially apparent. Or it might require abandoning or modifying quantum mechanics or general relativity. The paradox remains actively debated, with no consensus solution despite decades of brilliant work. From your perspective, falling toward the horizon, these abstract puzzles about information and quantum mechanics seem remote. You're facing immediate visceral realities, the acceleration, the distorted starlight, the growing shadow, the knowledge that you're approaching a point of no return. But these abstract questions will become concrete as you fall deeper. What happens to the information that constitutes you, your memories, your personality, your physical structure, when you cross the horizon? Is it preserved somehow, perhaps encoded on the horizon's surface, or is it genuinely lost, destroyed at the singularity, a true end rather than a transformation? You don't know. Nobody knows. The best minds in physics have debated these questions for decades without reaching consensus. As you fall, you're about to empirically test questions that theorists can only speculate about. Not that you'll be able to report your findings. That's the frustrating thing about black holes. They're the ultimate experiments we can never get results from. Anything you discover will die with you at the singularity, forever hidden behind the event horizon, inaccessible to science. But the journey continues regardless of its unknowable endpoint. You're falling faster now, the black hole larger, the distortions more extreme. Understanding what you're falling into doesn't change the trajectory, doesn't offer escape, doesn't alter the outcome. But it provides context, transforms terror into wonder, makes this forced journey into something approaching voluntary exploration. You're not just falling, you're discovering. You're experiencing conditions that no human has ever experienced, that no human could survive outside this thought experiment. You're visiting the most extreme environment the universe produces, the place where all our comfortable physics breaks down and reality reveals its true strangeness. The shadow grows larger, your velocity increases, and ahead, invisible but inevitable, the event horizon awaits. Time becomes a strange country. Distance 50,000 km. You've been falling for what feels like hours, though checking your watch, you see it's been less time than expected. The black hole dominates your view now, its shadow spanning nearly 60 degrees of your visual field, larger than 100 full moons would appear from Earth. The distortions of starlight create patterns that hurt to look at, geometries that your visual cortex wasn't designed to process. But it's time that's becoming truly strange. Not space. Space is warped, yes, but in ways you can see and somewhat comprehend. Time is betraying you in ways that are harder to grasp, that seem to violate causality itself, that create paradoxes your mind struggles to resolve. Your watch ticks forward steadily, 1 second per second, as it always has, as all watches must from their own perspective. Your heartbeat maintains its rhythm, your thoughts flow at their normal pace. Subjectively, internally, everything feels normal. Time is passing the way it always passes, moment following moment in orderly sequence. But if someone far from the black hole were watching you, say a friend in a spacecraft hovering safely at a distance of several million kilometers, they would see something entirely different. They would watch your movements slow down, your gestures would become languorous, dreamlike. If you waved your hand, the motion would take longer and longer from their perspective as you fell deeper into the gravitational well. Your watch, if they could see it, would appear to tick slower and slower compared to their own. This is gravitational time dilation, and it's not an optical illusion or trick of measurement. It's fundamental to how time works near massive objects. Time genuinely passes more slowly in stronger gravitational fields, not slower from your perspective. You always experience time at 1 second per second. But slower relative to observers in weaker gravitational fields. This effect has been measured on Earth. Atomic clocks, which keep time by counting oscillations of atoms, accurate to better than a second in hundreds of millions of years, run measurably faster on mountaintops than at sea level. The difference is tiny, just nanoseconds per day, but it's real and measurable. GPS satellites must account for this time dilation, or their positioning calculations would accumulate errors of kilometers within days. Near a black hole, the effect becomes dramatic. At your current distance, your watch runs perhaps 5% slower than a watch held by your distant friend. 5% might not sound like much, but it accumulates. If an hour passes for you, an hour and 3 minutes pass for them. If a day passes for you, 25 hours pass for them. The disconnect grows with every moment, and as you fall closer, the time dilation intensifies exponentially. By the time you reach the event horizon, the dilation becomes infinite. 1 second of your time corresponds to an infinite amount of time for the external observer. This creates a bizarre consequence. From their perspective, you never actually reach the horizon. They watch you approach asymptotically, slowing down, your image growing dimmer and more redshifted, but never quite arriving. Your last moment before the horizon is stretched into eternity from their viewpoint, but from your perspective, you will reach the horizon in finite time. You'll cross it, continue falling, experience what lies beyond. Both descriptions are true, both are valid. The resolution of this apparent paradox lies in understanding that now is not absolute. What happens now at the horizon from the external observer's perspective is not the same as what happens now from your perspective. The events are not synchronized. Time itself is relative. This relativity of simultaneity is one of the most profound and counterintuitive aspects of Einstein's relativity. In normal life, we assume that if two events happen at the same moment, everyone agrees they're simultaneous. If a clock strikes noon in New York and a clock strikes noon in London, surely those events are simultaneous. But they're not exactly. The simultaneity depends on the observer's motion. For someone moving at high speed relative to Earth, those events might not be simultaneous at all. One might happen before the other. Near a black hole, this relativity of simultaneity becomes extreme. The now at the horizon for someone far away corresponds to an infinite future time for you. Your crossing of the horizon, from your perspective, simply doesn't exist in the distant observer's now. It's infinitely far into their future. They will never see it happen, not because of any limitation of observation, but because the geometry of space-time itself puts your crossing beyond any moment of time they can experience, yet you will cross. The horizon is not an impenetrable barrier from your perspective. It's simply a boundary, and you'll pass through it as smoothly as crossing an invisible line. The contradiction is not a flaw in physics, but a revelation about the nature of time, that it's not a universal flow affecting everything equally, but a local property that depends on where you are and how you're moving. You try to wrap your mind around this. Your future, your crossing of the horizon, your journey to the singularity, your death, is so far in the future from the external observer's perspective that it's effectively infinite. If the distant observer waited forever, watched for eternity, they would never see you cross. Yet from your perspective, you'll cross in a matter of hours or days. How can both be true? The answer involves understanding that space-time near the horizon is so dramatically curved that light itself struggles to escape. Photons leaving your body, the light that would carry your image to the distant observer, must work against intense gravity. They climb out of the gravitational well, losing energy in the process, their wavelengths stretching, shifting toward red and then infrared, and then radio waves. As you approach the horizon, the photons leaving you are increasingly redshifted. Their frequency decreases, their energy drops. They arrive at the distant observer fainter and fainter. Eventually, they're redshifted to such low frequencies that they're undetectable, their wavelengths stretching to kilometers, then light years, becoming indistinguishable from the background radiation of space. Moreover, these photons take longer and longer to climb out of the gravitational well. A photon leaving you 1 second before you cross the horizon might take years to reach the distant observer. A photon leaving you 1 microsecond before crossing might take millennia. The photons from your final moment, the instant before the horizon, take infinite time to reach the outside universe. They never arrive. They're frozen in the geometry of space-time, forever climbing out of a well they can never escape. So the distant observer sees your image fade, redshift, slow down, but never disappear completely. Your last image before the horizon will persist for millions or billions of years, gradually dimming, gradually shifting to longer wavelengths, but always present. Long after you've crossed and died at the singularity, long after every atom of your body has been crushed to infinite density, your ghost will still hover at the edge of the horizon, visible in principle if not in practice. This creates strange implications for information, the information that constitutes you, your memories, your physical structure. The quantum states of every particle in your body seems to be preserved in some sense on the horizon, encoded in the pattern of red-shifted radiation still escaping. This is related to the holographic principle, the idea that all the information in a volume of space might be encoded on its boundary. From this perspective, you never really fall into the black hole. You're smeared across the event horizon, your information spread over its two-dimensional surface like a hologram. The you that crosses the horizon and falls to the singularity might be just one description of events, valid from your perspective but not from an external perspective. The you that's encoded on the horizon might be equally real, equally valid. Which description is correct? Both. Neither. The question might be meaningless. Different observers in different reference frames see different realities, and both realities are valid. This is not confusion or uncertainty, but insight into the nature of space-time. That reality itself is observer-dependent, that there is no single objective truth about what happens, only a collection of perspectives that are individually consistent, but collectively contradictory. You feel a slight discomfort now, a gentle pulling sensation. The tidal forces are becoming noticeable. Your feet, closer to the black hole, feel slightly heavier than your head. It's like hanging upside down, a pressure difference across your body that your cardiovascular system struggles slightly to compensate for. Blood wants to pool in your lower extremities. Your heart works a bit harder to pump blood to your head. This is still mild, manageable, not painful, but it's growing. These tidal forces, differences in gravitational pull across your body, increase exponentially as you fall closer. Eventually they'll become violent, overwhelming, fatal. But not yet. For now, it's just a reminder that you're in an extreme environment, that you're experiencing gravity gradients no human has ever felt. The physics behind tidal forces is simple in principle. Gravity decreases with distance, specifically with the square of distance. If your feet are a meter closer to the black hole than your head, they experience slightly stronger gravity. The difference is small at large distances but grows dramatically as you approach the horizon. Near the event horizon, the difference between the gravity at your feet and the gravity at your head becomes enormous. For a stellar mass black hole, say, one with 10 times the sun's mass, the tidal forces at the event horizon would be instantly fatal. The difference in gravitational pull across a human body would be millions of times your weight. You'd be torn apart, shredded into atoms before you reach the horizon. This process has been charmingly named spaghettification. You'd be stretched lengthwise while compressed sideways, elongated like a noodle until molecular bonds failed and you came apart. But for a supermassive black hole like Sagittarius A/M, the event horizon is so far from the center that the tidal forces there are surprisingly gentle. You can cross the horizon intact, conscious, still able to observe and think. The spaghettification comes later, deeper inside as you approach the singularity. This makes supermassive black holes far more interesting for our thought experiment. You get to experience the crossing, to witness the interior, to understand what happens inside the horizon before the tidal forces become fatal. You're aware that your time is limited, not just in the obvious sense that you're falling toward your death, but in a more subtle way. From your perspective, you have a finite amount of time remaining until you reach the singularity. That time might be hours or days depending on the black hole's size and your trajectory, but it's finite and calculable. The countdown has started. Every second that passes brings the singularity 1 second closer. Yet from the external perspective, you have infinite time. You'll never reach the singularity from their viewpoint because you'll never finish crossing the horizon. You exist in two contradictory temporal states simultaneously. Finite time remaining in your frame, infinite time remaining in the external frame. Both are true. Both are real. The contradiction is not a failure of logic, but a revelation about the nature of time near black holes. You wonder what your distant friend sees, if they're still watching. Do they see you frozen, motionless, hanging at the edge of the horizon? Do they see your image fading, reddening, dimming into invisibility? Can they see you at all anymore? Or has your image shifted so far into the infrared that you've effectively disappeared? The answer is that yes, they can still see you in principle, though it would require increasingly sophisticated detectors. Your image is still there, still broadcasting photons outward, but those photons are so redshifted now that they're radio waves, microwave radiation, eventually becoming indistinguishable from the cosmic microwave background. To see you, your friend would need radio telescopes, would need to filter out the background noise of the universe, would need to know exactly where to look and what frequency to listen to. And even then, they'd see you moving in extreme slow motion, each gesture taking years or decades to unfold. Time has become a strange country. It's no longer the universal river carrying everything forward at the same rate. It's fractured, shattered into a million perspectives, each experiencing duration differently, each seeing different sequences of events. Your time, the time measured by your watch and your heartbeat, marches steadily toward the horizon and the singularity beyond. External time, measured by distant observers, stretches your approach into an endless asymptotic approach that never concludes. Both are real, both are happening, and somewhere in the mathematics of general relativity, in the equations describing curved spacetime, both perspectives coexist without contradiction. The universe accommodates these multiple realities through the flexibility of spacetime itself, through the relativity of simultaneity, through the observer dependence of reality. The shadow grows larger still, the distortions intensify, and time, that seemingly simple one-dimensional progression from past to future, reveals itself to be far stranger than anyone imagined before Einstein. You're not just falling through space, you're falling through time, or perhaps time is falling through you, or perhaps the distinction between space and time is dissolving in this extreme environment where all the comfortable categories of experience break down. The event horizon approaches, time stretches, and you continue falling, carried forward by geometry itself, toward the ultimate mystery at the heart of the black hole. The light shows its true nature, distance 20,000 Hilansi. The universe behind you has transformed into something almost unrecognizable. The familiar constellations, the ones you've known since childhood, the patterns of stars that have guided sailors and inspired poets, are gone, warped beyond recognition by the intense gravitational lensing. The entire visible universe seems to be compressed into a shrinking circle behind you, as if all of creation is receding into a distant point. This is the optical manifestation of extreme space-time curvature. Light from the universe is being bent around the black hole in increasingly tight curves. Stars that should be beside you appear behind you. Light from galaxies at your back appears in front of you, having curved completely around the black hole to reach your eyes. The effect creates a surreal, impossible view. The entire cosmos seems to be wrapped around the shadow, concentrated in directions that make no geometric sense. Directly behind you, in the direction you came from if you turned around, you'd see something spectacular. The light from the entire universe you're leaving would be compressed into a bright ring, an Einstein ring of starlight surrounding the dark circle of the black hole's shadow. Everything that exists out there, billions of galaxies, trillions of stars, would be visible simultaneously, their light bent around the gravitational well, focused and concentrated. But that light is changing. The colours are shifting, becoming strange. Stars that should be yellow or red now appear blue, even violet. The spectrum is compressed toward higher frequencies, toward higher energies. This is gravitational blue shift, the opposite of the gravitational redshift that affects light climbing out of the gravitational well. You're falling into the well, and light falling with you is gaining energy, its wavelength compressing, its frequency increasing. The effect is dramatic and accelerating. Light that started as infrared radiation might now be visible red. Red light shifts to orange, to yellow, to green, to blue. The universe behind you is literally changing colour as you fall. the spectrum of all its radiation shifting uniformly toward higher energies. If you could continue falling indefinitely, visible light would shift to ultraviolet, then to X-rays, then to gamma rays, eventually becoming so energetic that it would be lethal. But there's another component to the light's behavior that's even more dramatic. The light is intensifying. It's growing brighter, more concentrated. This isn't just because you're seeing all the light from many directions simultaneously. It's because the photons themselves are gaining energy from falling into the gravitational well, and energy means brightness. The universe behind you is becoming a furnace of blue-shifted radiation. At the same time, the shadow ahead of you has become vast, filling most of your forward view. It's not just black, it's the blackest thing you've ever seen, a darkness so absolute it seems to have texture and weight. Your eyes keep trying to focus on it, to see detail in that darkness, but there's nothing to see. Its absence defined by presence, a void so complete that it becomes an object in itself. Around the shadow's edge, if the black hole is actively feeding, you see the accretion disk in all its terrifying glory. The disk is blindingly bright, even through the protective filters you're imagining you have. Material spiraling toward the event horizon is compressed and heated by friction to temperatures of millions of degrees. It emits across the entire electromagnetic spectrum: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. But from your perspective, this emission is further blue-shifted. The inner edge of the accretion disk, orbiting at significant fractions of light speed just outside the event horizon, appears insanely bright and shifted toward higher energies. What should be relatively cool visible light appears as scorching ultraviolet or soft X-rays. The disk has become a death ray, bathing you in radiation that would be instantly fatal to an unprotected human. The disk also exhibits strange visual properties caused by the extreme gravitational lensing. The part of the disk behind the black hole curves up and over, appearing above the shadow. You see it from both sides simultaneously, an impossible perspective that violates all intuition about how objects should look. The disk appears as a twisted halo around the shadow, wrapping over and under it, creating a complex three-dimensional structure that your visual cortex struggles to process. The side of the disk moving toward you, the approaching side of the rotation, blazes brighter than the side moving away. This relativistic beaming effect, caused by material moving at near light speeds, creates asymmetry in the disk's appearance. One side is perhaps 10 or 100 times brighter than the other, depending on the disk's rotation velocity. Combined with the gravitational lensing, the result is an image that seems more like abstract art than physical reality. You notice something else strange about the light. There's a directionality to it now, a sense that most of the radiation is coming from behind you rather than from all directions equally. This is because light falling into the black hole with you is being focused, concentrated toward the center. The geometry of space-time is becoming so curved that light rays are bending toward each other, converging. This convergence will eventually become extreme. Much closer to the singularity, in the final microseconds before your death, all light will converge to a single point ahead of you. You'll see the entire history of the universe flash before your eyes, literally. Light that fell into the black hole years ago, decades ago, billions of years ago, will all converge at the singularity at the same moment you reach it. You'll witness creation and apocalypse simultaneously. But that's still in the future. For now, the light is merely growing stranger, brighter, more concentrated. You're experiencing optical effects that no human has witnessed, that no human could witness outside this thought experiment. The universe is revealing how light behaves in extreme conditions, showing you the true flexibility of electromagnetic radiation when space-time itself is twisted into impossible configurations. You think about what light actually is. In everyday life, it seems simple: radiation that travels in straight lines, that reflects off surfaces, that can be focused with lenses. But near a black hole, light reveals its true nature as a phenomenon deeply coupled to the geometry of space-time. Light doesn't travel through space, it travels through space-time following geodesics, the equivalent of straight lines in curved geometry. Near the black hole, those geodesics are anything but straight in the ordinary sense. They curve, twist, spiral, converge. Light that starts travelling in one direction might end up travelling in a completely different direction, after bending around the gravitational well Some light orbits the black hole multiple times before either escaping or falling in. The photon sphere, the region where light can orbit, is littered with the ghosts of ancient photons, circling endlessly until some perturbation sends them inward or outward. You're also aware that your own body is emitting light, though you can't see it directly. You're at body temperature, around 310 Kelvin, which means you emit thermal radiation primarily in the infrared. These photons leaving your body carry information about you, about your temperature, your chemical composition, the quantum states of molecules in your skin. They climb out of the gravitational well, red-shifting as they go, eventually reaching distant observers as extremely low-frequency radio waves. But more and more of these photons are not escaping. As you fall closer to the horizon, an increasing fraction of the light leaving your body cannot escape. It falls back, pulled by gravity so strong that even electromagnetic radiation cannot overcome it. Your visible radius is shrinking, the distance from which you can be seen is decreasing. Soon you'll be invisible from the outside universe, not because you've crossed the horizon, but because light leaving you can no longer escape. This creates another time dilation effect. Light takes time to travel, and that time is affected by gravitational time dilation. The light leaving your body and travelling to distant observers is itself experiencing time dilation. It climbs out of the gravitational well slowly, taking longer and longer to make the journey. The image that distant observers see is not you in real time, but you in the past, with the delay growing longer as you fall deeper. Combined with the stretching of time from time dilation, this creates a double effect. Not only does your motion appear to slow down to external observers, but the light carrying your image takes longer to reach them. The combination causes your image to appear frozen at the horizon, preserved there for eternity from the external perspective. You experience none of this personally. From your perspective, light behaves normally, or as normally as it can in this bizarre environment. Photons leave your body at light speed, as they always have. Time passes at 1 second per second. The strangeness is all relative, all dependent on comparing your reference frame to distant reference frames in different gravitational conditions. The accretion disk suddenly flares, if one exists in your scenario. A clump of matter, perhaps the torn-apart remnant of a star that wandered too close years ago, spirals into the final plunge. As it crosses the innermost stable circular orbit, the point beyond which no stable orbits exist, it accelerates catastrophically, friction heating it to billions of degrees. The emission spikes across all wavelengths simultaneously. From your perspective, this flare is blue shifted to extreme energies. What might be intense X-rays from an external viewpoint appears to you as gamma rays, the most energetic electromagnetic radiation possible. The burst lasts just seconds from your perspective, a blazing moment of violence as matter makes its final scream before crossing the horizon and disappearing forever. You realize that if you could see your own body from outside, if you had a camera transmitting images to a distant observer, you'd see yourself bathed in this light, illuminated by the death throes of matter falling into the abyss. But the image they'd see would be old, increasingly out of date, showing you not as you are, but as you were minutes or hours ago. The real-time you is already much closer to the horizon, already much deeper in the gravitational well, already much closer to the point of no return. The light around you has become a plasma of blue-shifted radiation, a storm of photons with nowhere to go but inward. You're swimming in a sea of electromagnetic energy, all of it falling with you, all of it converging toward the singularity. The universe behind you blazes with impossible brightness. The shadow ahead has become almost all you can see, a vast darkness waiting to swallow you. And through it all, the light tells its story. The story of space-time curvature, of gravitational potential, of the deep connection between geometry and electromagnetism. Light is not just illumination, it's information, carrying messages about the structure of reality itself. And in this extreme environment, those messages are clear. You're approaching the point where normal physics ends and something else, something stranger, something we don't fully understand, begins. The event horizon is close now, very close, and light, that most familiar of physical phenomena, has revealed itself to be far stranger than you ever imagined. The tides begin to pull, distance 10,000 kilometers. You've been aware of the tidal forces for a while now, that gentle pulling sensation differentiating your feet from your head. But gentle is no longer the right word. The forces are growing, intensifying, becoming uncomfortable. Your feet feel distinctly heavier than your head now, as if you're hanging upside down with weights attached to your ankles. Your cardiovascular system is working harder, struggling to pump blood against this gradient. The physics behind what you're feeling is simple but relentless. Gravity decreases with distance following an inverse square law, double the distance, and gravity drops to 1/4. Your feet, being closer to the black hole's center than your head, experience stronger gravity. For a person 2 meters tall, this difference is normally negligible. On Earth, the gravity at your feet versus your head differs by an amount too small to notice. But near a black hole, the gradient becomes steep. At your current distance, still thousands of kilometers from the event horizon, the difference is already noticeable. Your feet might experience gravity perhaps 10% stronger than your head. That doesn't sound like much, but 10% of the immense gravity you're experiencing is a substantial force. It's enough to create real discomfort, enough to strain your body's ability to maintain blood circulation and structural integrity. And it's accelerating. The tidal forces grow exponentially as you fall closer. Every kilometer of descent increases the gradient significantly. What's uncomfortable now will become painful soon, then agonizing, then instantly fatal. The question is not whether the tidal forces will kill you, but when, before you reach the horizon or after you cross it. For Sagittarius A, with its enormous mass, the answer is after. The event horizon is so far from the center, 12 million kilometers, that the gradient there is surprisingly gentle. You can cross intact, still conscious, still able to observe and think. But once inside, as you continue falling toward the singularity, the gradient will steepen catastrophically. Long before reaching the singularity, the tidal forces will exceed any material's ability to resist them. You're beginning to understand what spaghettification really means. It's not metaphor or analogy. It's literal description of what happens when tidal forces become extreme. Your body will be stretched lengthwise, head pulling away from feet, feet pulling away from center, while being compressed sideways. You'll become literally noodle-shaped, elongated like spaghetti, hence the term. But it's worse than simple stretching. The forces don't just pull you apart as a rigid object. They pull on every part of you individually. Your skin stretches, your muscles elongate, your bones are pulled like taffy, your organs distort. At the cellular level, cells are stretched until membranes rupture. At the molecular level, the bonds holding molecules together are strained and broken. At the atomic level, eventually even the electromagnetic forces holding atoms together will be overcome. You'll be reduced to a stream of atoms, then subatomic particles, a one-dimensional string of matter falling toward the singularity. This is your inevitable fate, the end that awaits every piece of matter that falls into a black hole. Complexity is destroyed, structure is eliminated, everything becomes a linear chain of fundamental particles spiraling toward infinite density. But you're not there yet. Currently the discomfort is manageable, if unpleasant. You feel stretched, strained, like you're on a medieval rack being slowly pulled apart. Your back aches, your neck hurts. Blood pools in your lower body despite your heart's efforts. You feel lightheaded, dizzy as blood flow to your brain becomes inadequate. You try to curl into a ball, minimizing the distance between different parts of your body, reducing the tidal gradient across yourself. It helps slightly. By bringing your feet closer to your head, you reduce the differential in gravitational force between them. But you can't eliminate it completely, and as you fall closer, even a curled position won't help. The forces will grow beyond your ability to resist them regardless of posture. You notice something else disturbing. Your body is creaking, literally creaking, the way old floorboards creak under weight. These are your joints, your bones, your tendons protesting the strain. Your skeleton is being pulled in ways it was never designed to handle. Human bones are strong in compression. They can support body weight, can withstand impacts, but they're weaker in tension, in pulling. The tidal forces are pulling, stretching, and your bones are complaining audibly. Your breathing becomes difficult. The tidal forces affect your lungs, pulling them lengthwise, making it hard to expand them sideways. Each breath requires conscious effort. Your diaphragm struggles against the forces trying to stretch your torso. You feel like you're suffocating, not from lack of oxygen. There's no oxygen in space anyway, and we're imagining you're somehow protected from vacuum, but from inability to mechanically inflate your lungs. Your heart is working overtime, beating faster, pumping harder. It's trying to circulate blood through a cardiovascular system that's being stretched like a rubber band. The pressure gradients are wrong. Blood wants to flow toward your feet, pooling there, draining from your head. Your heart fights this, but it's a losing battle. You feel increasingly faint, consciousness wavering as blood flow to your brain drops. You wonder how much longer you can remain conscious, how much longer before the tidal forces incapacitate you, render you unable to observe or think. You want to witness the crossing of the event horizon, want to see what lies beyond, want to understand what happens inside. But if you lose consciousness before crossing, you'll miss the most important part of the journey. The universe behind you is now compressed into a tiny circle of intensely bright light. The entire cosmos focused into a spot perhaps 10 degrees across, the size of your fist at arm's length. All the stars, all the galaxies, everything visible, reduced to a brilliant point of blue-shifted radiation so intense it hurts to look at even indirectly. The rest of your view is dominated by the shadow, by the vast darkness that's now nearly all you can see. You realize that your own body is being stretched visibly now, looking down at yourself, difficult because of the forces on your neck. You see that you're elongated, your proportions wrong, your legs look too long, your arms are thin and stretched. It's like seeing yourself in a funhouse mirror, except this distortion is real, happening to your actual body, not just to your reflection. The pain is intensifying. What was uncomfortable is becoming painful. What was painful is becoming agonizing. Every muscle in your body is screaming. Your joints feel like they're being pulled apart. Your spine feels like it's being stretched on a rack. This is still just the beginning of spaghettification, still the gentle phase, but it's already more pain than you've ever experienced. You try to distract yourself by thinking about the physics. The tidal force on your body can be calculated if you know the black hole's mass and your distance from it. The force differential across your body grows as the cube of decreasing distance. Half the distance means 8 times the tidal force. This cubic relationship explains why the forces grow so quickly, why gentle discomfort becomes lethal violence over relatively small changes in position. For a human body 2 meters long, the tidal force at the event horizon of Sagittarius A is actually quite modest, perhaps comparable to hanging upside down, uncomfortable but survivable. But just 1,000 kilometers deeper inside the horizon, the force increases dramatically, 10,000 kilometers deeper, still far from the singularity, and you'd be pulled apart. The lethal radius for a human body in this black hole is probably somewhere around a few thousand kilometers inside the horizon. That gives you time. Not much time measured in your own experience, but enough to cross the horizon conscious, to observe what lies beyond, to witness the interior before the forces become unsurvivable. How long do you have? Hours maybe, if you're lucky. Minutes if you're not. The fall is accelerating, the tidal force is growing exponentially, and your body has limits that are rapidly approaching. You notice your watch is behaving strangely. No, not behaving strangely. It's ticking normally, 1 second per second as always. But you're comparing it mentally to what you imagine a distant watch would read, and the comparison has become almost meaningless. The time dilation is so extreme now that the concept of simultaneous has broken down completely. Your time and external time have diverged to the point where they're measuring fundamentally different things. The pain spikes suddenly as you encounter a slight irregularity in your trajectory, a small change in the gradient as you fall through a region where the space-time curvature varies slightly. It's a reminder that this fall is not smooth and predictable, but chaotic and violent, subject to fluctuations and variations you can't anticipate or control. Your vision is starting to blur, going dark at the edges. Tunnel vision, caused by inadequate blood flow to your retinas. Your brain is being starved of oxygen, not because there's no oxygen to breathe, but because your heart can't pump blood against these tidal forces effectively enough. Consciousness is slipping. You fight to stay awake, to remain aware. You've come this far, fallen this deep, endured this much. You will not miss the crossing. You will witness the event horizon. You will see what lies beyond. If you can just hold on a little longer, stay conscious through the pain and the disorientation and the physiological collapse, you'll achieve something no living being has ever achieved. Conscious experience of crossing a black hole's event horizon. The shadow fills your vision completely now. There's nothing else to see except that vast darkness ahead and the tiny point of light behind. The universe has reduced to binary, light and dark, outside and inside, past and future. You're at the threshold, approaching the boundary between what is knowable and what is forever hidden, between the universe of cause and effect and the region where causality itself breaks down. The tidal forces pull harder, your body screams, and the event horizon rushes up to meet you. Crossing the point of no return, the event horizon. This is the moment, the event horizon, the point of no return, the boundary between our universe and the hidden interior of the black hole. For months or years of planning this thought experiment, for hours of falling, everything has been building toward this instant. You're about to cross the most significant boundary in the universe, more significant than any border between countries, any boundary between Earth and space, any threshold between the known and unknown. And yet, as the moment arrives, it's anticlimactic. There's no barrier. No membrane, no sensation of crossing, no feeling of transition. One moment you're outside the event horizon, the next you're inside, and there's no clear instant when the crossing occurs. It's smooth, continuous, unremarkable. You expected something, a tingle, a sensation, a moment of awareness that you'd passed the point of no return. But there's nothing. The crossing feels like nothing at all. It's like crossing the equator while flying in a plane, an event of enormous significance that produces no direct sensation whatsoever. This is simultaneously reassuring and terrifying. Reassuring because it means the horizon is not a physical barrier that will destroy you. Terrifying because it means you've crossed without even knowing exactly when. You're inside now, inside the black hole, in the region from which no escape is possible, from which no information can be transmitted, from which no path leads back to the outside universe. How do you know you've crossed? You can't know for certain, not immediately. There's no sign, no marker, no indication. But you can infer it from observations. The universe behind you has compressed to an impossibly small point now. The entire cosmos reduced to a spot of brilliant blue shifted light. The shadow, or what was the shadow, now fills your entire forward view. You're not looking at the shadow anymore, you're inside it. The geometry has changed fundamentally, though it's hard to perceive directly. Outside the horizon, the radial coordinate, the direction toward the center, is a spatial dimension. You have freedom to move inward or outward, even though the gravity makes outward motion difficult or impossible depending on your velocity. Inside the horizon, that radial coordinate has become time-like. Moving toward the singularity is not a choice, but a progression through time, as inevitable as moving from present to future. This transformation is the key to understanding why escape is impossible. It's not that you lack a powerful enough rocket. It's not that you'd need to travel faster than light, though you would. It's that outward has ceased to be a direction in space. It's become a direction in time, specifically a direction toward the past. Escaping the black hole would require traveling backward in time, which is forbidden by causality. Think of it this way. In normal space, you can move forward and backward. You can go somewhere and then return. But you cannot move backward in time. You cannot return to yesterday. The future is a one-way direction, and you're forced to move through it at a steady rate. Inside the event horizon, the radial direction has become like time, one way, inexorable, unavoidable. You must move toward the singularity just as you must move toward tomorrow. The singularity is now your future, not a possible future, not a probable future, but your certain, unavoidable future. It's as inevitable as next Tuesday. Every path through space-time, every possible action you could take, every conceivable trajectory leads to the singularity. There are no paths that lead back out, no paths that avoid the singularity, no paths that lead anywhere else. Your fate is sealed, written into the geometry of space-time itself. This inevitability is the most profound aspect of being inside a black hole. Outside, you had options. You could accelerate, decelerate, change trajectory. You had freedom of movement, even if that freedom was constrained by the intense gravity. Inside, you have no freedom. You're on rails, following the only path that exists, heading toward the only possible destination. How long do you have? From your perspective, from the time measured by your watch and your subjective experience, The answer depends on the black hole's mass and your exact trajectory. For Sagittarius ACM, assuming you cross the horizon at high velocity, you probably have hours remaining, maybe a day if you're lucky. Not much time, but enough to observe, to think, to try to understand what's happening. But time remaining is a complicated concept here. Remaining until what? Until the singularity? Yes, that's finite and calculable. But from the perspective of the outside universe, you have infinite time remaining. You never reach the singularity from their viewpoint because you never finish crossing the horizon. Your interior journey doesn't exist in their frame of reference. It's infinitely far in their future. So you exist in a strange temporal state. Finite time remaining in your own frame, infinite time remaining in the external frame. Both descriptions are valid, both are true. The paradox resolves through understanding that there is no universal now that spans both reference frames. Your now and their now have diverged completely, separated by the infinite gravitational time dilation at the horizon. You look around, trying to understand what you're seeing. The visual experience inside the horizon is bizarre beyond description. The universe behind you, the entire outside cosmos, is compressed into an impossibly bright point of light. All the photons that have been falling in behind you, all the light from stars and galaxies, all the radiation from billions of years of cosmic history is converging toward that same point you're heading to, the singularity. This convergence creates a strange effect. You can see your past, light that reflected off you before you crossed the horizon, light that tried to escape but couldn't, light that's been falling along geodesics similar to yours. All of it is here with you, converging toward the center. In principle, if you could look carefully at that point of light behind you, you might see images of yourself from minutes or hours ago, frozen photons that captured your appearance outside the horizon. The geometry here is so distorted that space-time diagrams, the usual way physicists visualize these situations, break down. Outside the horizon, space and time form a four-dimensional continuum with 3 space dimensions and 1 time dimension. You can draw diagrams showing spatial positions at different times, showing world lines, the paths objects take through space-time, as curves on these diagrams. Inside the horizon, the diagrams still work mathematically, but they're nearly impossible to interpret intuitively. The radial direction has become time-like, meaning it should be drawn as a time axis. But it still looks spatial. The result is confusing, counterintuitive, resistant to visualization. You can do the mathematics, can write the equations, can solve for trajectories, but understanding what those solutions mean physically is profoundly difficult. You feel a strange mixture of emotions. Terror, certainly. You're falling toward your death, toward a singularity where you'll be crushed to infinite density. But also wonder, awe, even a kind of peace. You're experiencing something no human has experienced. You're in a place no human has been. You're witnessing conditions that push physics to its absolute limits and beyond. There's privilege in this, even as there's doom. The tidal forces continue to intensify. The pain is constant now. No longer spiking, but sustained at a level that would be unbearable if you weren't so focused on observing, on understanding, on experiencing every moment of this impossible journey. Your body is noticeably elongated, stretched like taffy, your proportions grotesquely distorted. You look like something from a surrealist painting, human but wrong, recognizable but alien. Your consciousness is flickering, dimming. The blood flow to your brain is inadequate. You're experiencing hypoxia, oxygen starvation. Even though oxygen supply isn't the problem, the delivery mechanism is failing. Your cardiovascular system cannot overcome these tidal forces. You're going into shock, multiple organ systems beginning to fail simultaneously. But you're still aware, still conscious, still able to observe and think even if those processes are becoming sluggish, difficult. You've made it this far. You've crossed the event horizon conscious and aware. That's an achievement of sorts, even if there's no one to report it to, no way to communicate what you've learned. You wonder what would happen if you tried to send a signal out, if you had a radio transmitter, if you broadcast a message toward the outside universe. What would happen to that signal? The answer is simple and absolute. Nothing. The radio waves would propagate outward at the speed of a light, which sounds promising. but outward is now a direction in time, specifically a direction toward the past. The radio waves would be trying to travel backward in time, which is impossible. They would follow geodesics that curve back inward, that redirect them toward the singularity. Your message would never escape. It would never reach the outside universe. It would fall to the singularity along with you. This is what it means to be beyond the event horizon. Not just that escape is difficult, but that escape is literally meaningless. A direction that doesn't exist. A path that leads nowhere because there is no where to lead to. The outside universe still exists, but you cannot reach it, cannot affect it, cannot send information to it. You've become causally disconnected from the cosmos you came from. Yet paradoxically, information about you still exists outside. Your image is still visible, frozen at the horizon from the external perspective. The information that constitutes you, your memories, your personality, the quantum states of every particle that makes up your body, is encoded somehow in the pattern of radiation at the horizon. You exist in two places simultaneously, as a physical being falling toward the singularity and as information encoded on the two-dimensional event horizon. This duality is at the heart of the black hole information paradox. Are you inside the black hole, falling toward the singularity soon to be destroyed? Or are you on the horizon, encoded as information preserved in some form? The answer appears to be both, different descriptions of the same reality from different perspectives. Neither description is more true than the other. Some physicists, led by Leonard Susskind and Gerard 't Hooft, developed the holographic principle from this insight. They proposed that all the information in a three-dimensional volume of space can be encoded on its two-dimensional boundary like a hologram. The interior of the black hole might be described completely by information on the event horizon. Your interior journey might be just one way of describing information that's actually stored on the horizon's surface. This idea has profound implications beyond black holes. It suggests that our entire universe might be holographic, that everything we experience in 3 dimensions might be encoded on a 2-dimensional surface at the cosmos's edge. The physics happening around us might be a projection from information stored on a distant boundary. We might be living in a cosmic hologram. But these are abstract ideas, theoretical speculations. Your experience is immediate and physical. You're being torn apart by tidal forces. You're falling toward a singularity that will crush you to infinite density. The holographic principle, however elegant, doesn't change your subjective reality. The point of light behind you is beginning to change, to evolve. It's not just bright anymore, it's structured, layered, containing complexity. You're seeing deeper into cosmic history as you fall. Light that entered the black hole years ago, decades ago, is converging at the singularity along with you. You're witnessing a compression of time, all of history focused into a single point. The horizon is behind you now, forever behind you. You've crossed it, you're inside, and there's no going back. Not just no practical way back, no technological solution, no clever trick. There's literally no back to go to. The horizon exists in your past, and you cannot travel to your past any more than you could yesterday morning. You're alone in a way no human has ever been alone. Cut off not just from other people, but from the entire universe. No signal you send will ever be received. No thought you think will ever be known. You've crossed into absolute privacy, absolute isolation. Whatever you experience from now until the singularity will be experienced by you alone and will die with you. This loneliness is cosmic, final, complete. It should be terrifying, and perhaps it is, but there's also something peaceful about it. No expectations, no obligations, no one watching or judging. Just you and the universe in its most extreme form, engaged in a final dialogue that only you will hear. The singularity awaits, growing closer not in space but in time. Every second that passes brings it 1 second nearer. You can calculate when you'll reach it, can mark off the remaining moments like a countdown. The clock is ticking, and no force in the universe can stop it. You've crossed the point of no return. You're inside the black hole, and ahead lies the final mystery, the singularity itself, where all our physics fails, where space and time end, where reality reaches its ultimate limit. The journey continues inward. The journey continues toward whatever lies at the end of everything, the interior. where space becomes time. Inside the event horizon, you exist in a place that no light has ever left, that no information has ever escaped from, that is forever hidden from the outside universe. This is the interior of the black hole, the most mysterious region in all of physics, accessible in principle, but forever beyond observation, described by mathematics, but resistant to intuition. The first thing to understand is that you're not in some exotic parallel dimension or alternate universe. You're still in the same space-time you've always inhabited, still subject to the same laws of physics, general relativity, quantum mechanics, conservation laws. What's different is the geometry. The curvature of space-time has become so extreme that it creates properties and behaviors utterly unlike anything in normal space. The most profound difference is the transformation of the radial direction. Outside the horizon, the direction toward the black hole's center is spatial. It's a direction in space you can move through, like north or south, up or down. You have freedom to move inward or outward, though gravity makes outward motion difficult. Inside the horizon, this changes fundamentally. The radial direction becomes temporal. It's no longer a direction in space, but a direction in time, specifically toward the future. Just as you cannot stop moving forward in time, you cannot stop moving inward toward the singularity. Just as you cannot move backward in time to yesterday, you cannot move outward away from the singularity. The singularity is not a place you might reach. It's a time you will reach. This is not metaphor or analogy. The mathematics of general relativity shows clearly that inside the horizon, the coordinate that measures distance from the center becomes time-like rather than space-like. In the equations describing space-time geometry, the radial coordinate swaps properties with the time coordinate. Space and time exchange roles. What does this mean experientially? It means that asking, how far am I from the singularity, is like asking, how far am I from next Tuesday? Distance has become duration. The singularity is not 30,000 kilometers away, it's 3 hours away, or however long until you reach it. You measure your separation from the singularity in time, not space. You try to make sense of your surroundings, but it's difficult. The visual field is dominated by that point of brilliant light behind you, containing all the light from the outside universe, all the photons that have been falling in compressed into a single bright spot. It's painfully bright even through closed eyelids, even when you turn away. There's nowhere to hide from it because it's not really coming from a specific direction. It's converging toward the same point you're heading toward, the singularity. The darkness ahead has changed character. It's no longer the shadow of the event horizon. You've crossed that boundary. Now it's something else, something more fundamental. It's the direction toward your future, toward the singularity, toward the end of space-time itself. Looking in that direction is like looking into the future, which makes a strange kind of sense given that the radial direction has become temporal. The geometry here admits strange possibilities that don't exist outside. In principle, there could be closed time-like curves, paths through space-time that loop back on themselves, allowing an object to return to its own past. These would permit time travel in a literal sense, creating all the paradoxes that notion implies. Whether such curves actually exist inside realistic black holes remains debated. The mathematics allows them in some solutions, but nature might forbid them through quantum effects or other mechanisms we don't fully understand. You're also inside what's called the Cauchy horizon for a rotating black hole, a second boundary beyond the event horizon where determinism breaks down. Outside the Cauchy horizon, the laws of physics allow you to predict the future from the present, at least in principle. Inside the Cauchy horizon, this breaks down. The past doesn't determine the future uniquely. Multiple different futures become possible from identical starting conditions. But you're falling into a non-rotating black hole for simplicity, so there's no Cauchy horizon in your scenario. There's just the event horizon you've crossed, and the singularity ahead. The geometry is simpler, though no less fatal. The tidal forces are becoming severe. Your body has stretched visibly, elongated like a piece of pulled taffy. You're perhaps half again as tall as you were, but correspondingly thinner. Your organs are distorted, failing. Blood vessels are rupturing. Bones are cracking under the strain. You're being spaghettified in real time, transformed from a three-dimensional human into a one-dimensional string of matter. The pain has transcended anything you've experienced or imagined. It's not pain in specific locations anymore, but a total systemic agony, every cell screaming, every molecule protesting, every atom being stressed beyond its limits. You're aware that death is imminent, not at the singularity, but before you reach it, because your body will fail, will come apart, long before you reach that final point. You're beginning to lose coherence as a macroscopic object. Parts of you that were connected, cells that form tissues, molecules that form structures, are being pulled apart. You're becoming a cloud of particles, a stream of atoms falling in formation toward the singularity. The complexity that made you human, the organization that made you a living being, the structure that made you an individual, all of it is being erased by the relentless tidal forces. But you're still conscious. Somehow, impossibly, fragments of your brain are still functioning, still processing information, still generating the subjective experience of awareness. The neurons are stretched, distorted, failing, but they're firing one last time, creating one last moment of consciousness before the darkness. In this moment, you perceive something strange. The universe behind you, that point of converging light, is beginning to replay history. Not your personal history, but cosmic history. The history of all the matter and energy that's fallen into this black hole since it formed. Light from stars that fell in billions of years ago, if this black hole is that old, is converging at the singularity at the same moment you're arriving. You're witnessing the entire past of the black hole compressed into a single instant. Some theoretical physicists have suggested that the singularity might not be a point but a moment, an instant of time where all infalling matter and energy arrive simultaneously. In this view, the singularity is not a location but an event, a time when everything that ever fell in reaches the center together. You're approaching that moment, that final instant when past and future collapse into a single point. The mathematics describing the interior becomes increasingly strange as you approach the singularity. The curvature of space-time, measured by quantities called the Ricci scalar and the Kretschmann scalar, approaches infinity. These mathematical infinities signal the breakdown of classical general relativity. The theory that successfully described your fall from outside the horizon to this point is failing, producing nonsensical results. At the singularity itself, the theory fails completely. Density becomes infinite, curvature becomes infinite, tidal forces become infinite. Infinities in physics usually mean, I don't know what happens here. They're the theory's way of admitting defeat, of acknowledging that some new physics, probably quantum gravity, probably something involving both general relativity and quantum mechanics, is needed to describe what actually occurs. Some physicists speculate that quantum effects might prevent the formation of true singularities. Perhaps at scales approaching the Planck length, about 10 to 35 meters, the smallest distance that has meaning in quantum gravity, space-time itself becomes discrete, granular, preventing infinite compression. Perhaps the singularity is replaced by some quantum structure we don't yet understand. Others suggest that the singularity is real, that it represents a genuine end of space-time, a boundary beyond which nothing exists, not space, not time, not physical reality in any form we can comprehend. In this view, reaching the singularity means ceasing to exist in the most complete sense possible, not just dying but being removed from space-time entirely. String theory offers another perspective. In string theory, particles are not point-like, but extended one-dimensional objects, strings vibrating in higher dimensional space. As you approach the singularity, these strings might be stretched to their limits, until the theory's predictions change dramatically. Some string theorists suggest that black holes might contain entire universes, with the singularity serving as a connection to other realms of existence. But these are speculations, untested, and perhaps untestable. The singularity is hidden behind the event horizon, protected by cosmic censorship. No information about what happens there can reach the outside universe. No experiment can probe it. It remains the greatest mystery in physics, a place where our best theories fail, where questions multiply faster than answers, where the universe might be showing us the limits of what can be known. You realize you'll never know the answer. You'll reach the singularity. You'll experience whatever happens there, but you'll never be able to tell anyone. The knowledge will die with you. Or perhaps there is no knowledge because there's no there to know about, no experience to have, just an ending absolute and final. Your consciousness is fracturing now, fragmenting as your brain tissue pulls apart. Neurons that were millimeters apart are now centimeters apart, then meters, their connections severed by the tidal forces. The electrical signals that constituted thought are interrupted, scattered, lost. The coherent patterns that made you a thinking being are dissolving into chaos. In your final moments of awareness, you experience something profound and inexplicable. A sense of unity with the cosmos, perhaps, or a glimpse of something beyond space-time. Or maybe it's just neurons misfiring as they die, creating random sensations that your fragmenting consciousness interprets as revelation. The light converges, the darkness ahead becomes absolute, and the singularity, that point of infinite curvature where space-time ends, rushes toward you, or you toward it, with the inevitability of the future itself. You're inside the black hole, falling through the strangest geometry in the universe, approaching the ultimate mystery at the heart of existence. What happens next will determine whether the singularity is the end of everything, or the beginning of something beyond our comprehension. Spaghettification, the stretching of reality. The tidal forces have reached catastrophic levels. Your body, which crossed the event horizon more or less intact, is now being systematically destroyed by the difference in gravitational pull between your head and your feet. This is spaghettification in its full, terrible reality. Not a metaphor, not hyperbole, but a literal description of what's happening to you. Your height, which was perhaps 2 meters at the start of this journey, has increased dramatically. You're now 3 meters tall, 4 meters, 5 meters, and stretching further with every passing second. But this increase in height comes at a terrible cost. Your width is decreasing proportionally. You're being stretched lengthwise while being compressed from the sides, transformed from a human shape into something resembling a noodle or strand of spaghetti, hence the term. At the macroscopic level, your body structure is failing. Your skeleton, designed to support a body with certain proportions, cannot handle these new forces and dimensions. Bones are pulled apart at the joints, vertebrae separate from each other, your spine elongating beyond anything evolution prepared it for. Your skull is being pulled away from your neck from your shoulders from your torso, each connection stressed beyond its breaking point. Your soft tissues fare even worse. Muscles designed to work across certain distances are being stretched to many times their normal length. Muscle fibers tear, unable to maintain integrity across these impossible distances. Tendons snap, ligaments rupture. The connective tissue holding your body together as a coherent structure is failing systematically, unable to resist these gravitational gradients. Your organs are being distorted beyond recognition. Your heart, trying desperately to pump blood through a cardiovascular system that's meters longer than it should be, is itself being stretched, its chambers distorted, its valves pulled out of alignment. Blood vessels elongate, thin, rupture. Your lungs are stretched vertically, making breathing impossible even if there were air to breathe. Your digestive system, stomach, intestines, liver, kidneys, all are being pulled into long, thin approximations of their normal forms. At the cellular level, the destruction is even more complete. Cells that were adjacent, that communicated through chemical signals and physical connections, are being separated. The extracellular matrix holding tissues together is tearing apart. Cell membranes, stretched beyond their elastic limits, are rupturing, spilling their contents into spaces that are no longer properly spaces, but elongating voids. The neurons in your brain, those delicate cells responsible for consciousness and thought, are being pulled apart. Axons, the long fibers that transmit electrical signals between neurons, are being stretched until they snap. Synapses, the connections between neurons where communication happens, are being pulled apart, severing the links that make thought possible. The network that constituted your mind is being systematically dismantled by forces no neural tissue could possibly withstand. Yet somehow, fragments of consciousness persist. Not coherent thought anymore, not the organized mental processes you're familiar with, but flashes of awareness, moments of perception, brief sparks of sensation. Perhaps some neurons are still firing, still generating electrical activity, even as they're pulled apart. Perhaps consciousness is more resilient than it seems, persisting at the edge of destruction. Or perhaps what you're experiencing now isn't really consciousness in any meaningful sense, but just random neural activity that feels like consciousness. Patterns firing in a dying brain that create the illusion of continued awareness. There's no way to know, no external reference point to compare against. No observer who could determine whether your subjective experience is genuine or merely the last gasp of a failing nervous system. At the molecular level, even chemical bonds are being stressed. The molecules that make up your body, proteins, lipids, nucleic acids, carbohydrates, are being stretched. Covalent bonds, the strong bonds between atoms within molecules, are being pulled. Most of these bonds will hold, at least for now. Chemical bonds are strong, capable of resisting substantial force, but the weaker bonds, hydrogen bonds, ionic bonds, van der Waals forces, are failing. These are the bonds that give proteins their three-dimensional shapes, that hold DNA strands together, that organize molecules into the complex structures necessary for life. As these bonds break, molecules unfold, denature, lose their functional conformations. Proteins become long chains of amino acids rather than carefully folded functional units. DNA double helices unwind. The molecular organization that distinguishes living matter from mere chemistry is being erased. You're becoming less complex with every passing moment. The organization that made you a living being, that made you human, that made you an individual with memories and personality and thoughts, all of it is being stripped away layer by layer. First, the loss of behavior and coherent action, then the loss of consciousness and subjective experience, then the loss of cellular structure, then the loss of molecular organization. You're being reduced from a human to a collection of biological material, and soon from biological material to mere atoms. At the atomic level, matter is holding together for now. The electromagnetic forces that bind electrons to nuclei, that hold atoms together despite the tidal forces, are immensely strong compared to gravity at these scales. An atom is mostly empty space. The nucleus is tiny compared to the orbits of electrons, but the forces holding this structure together can resist enormous stress. But you're approaching limits even for atomic structure. The tidal forces are still growing, still intensifying, approaching magnitudes where even electromagnetic forces will be overcome. Eventually, if you could survive long enough, if you could continue falling close enough to the singularity, even atoms would be pulled apart. Electrons would be stripped from nuclei, the atoms themselves would be ionized, transformed into plasma of separated electrons and nuclei, and deeper still, even atomic nuclei might be disrupted. Nuclei are held together by the strong nuclear force, the most powerful force in nature, binding protons and neutrons into stable configurations. But at the singularity, even this force might be insufficient. Tidal forces might grow strong enough to pull apart atomic nuclei, to separate the fundamental particles, to reduce matter to its most basic constituents. You would become a stream of fundamental particles, quarks, electrons, photons, falling toward the singularity in single-file formation, a one-dimensional string of matter containing no structure, no organization, no information about what you once were. All the complexity of life, all the organization that evolution produced over billions of years, all the structure that made you uniquely you, erased completely, reduced to indistinguishable particles that could have come from anywhere, that carry no record of their history. This is the final violence of the black hole. Not just death, but complete obliteration. The destruction not just of life, but of structure itself. The reduction of complexity to simplicity, of order to chaos. You don't just die in a black hole, you're erased, unmade, disintegrated down to fundamental particles that carry no trace of what they once composed. The process is eerily similar to what happens in the universe's final fate according to some cosmological models. In the far future, assuming dark energy continues its current behavior, the universe might experience what's called heat death or the big freeze. All structure would gradually break down, stars would exhaust their fuel, black holes would evaporate through Hawking radiation. Eventually, even atoms might decay, leaving nothing but a thin soup of fundamental particles in an eternally expanding universe. Spaghettification in a black hole is like experiencing heat death in fast forward, compressed from trillions of years into seconds or minutes. You're witnessing the end state of matter, the ultimate fate awaiting all structure in the universe, but concentrated and accelerated beyond comprehension. Some physicists have wondered whether information can truly be destroyed by this process. In quantum mechanics, information is supposed to be conserved. The state of a system at one time determines its state at all future times. But how can information be conserved when you're being reduced to indistinguishable fundamental particles? Where does the information about what you were go? This is related to the black hole information paradox we discussed earlier. When matter falls into a black hole and is destroyed at the singularity, is information lost? Or is it preserved somehow, perhaps encoded in the Hawking radiation eventually emitted by the black hole, or in correlations we don't yet understand? The holographic principle offers one possible answer. Your information was never really inside the black hole. It was encoded on the event horizon from the moment you crossed. The interior journey, the spaghettification, the destruction at the singularity, these might be just one description of events, valid from your interior perspective but complementary to the exterior description where you're smeared across the horizon's surface. In this view, you exist in two forms simultaneously, as a three-dimensional being experiencing spaghettification and death in the interior, and as information encoded on the two-dimensional event horizon. Neither description is more fundamental than the other. They're different perspectives on the same reality, like how a hologram can show different images depending on the viewing angle. But these theoretical considerations offer no comfort to your shredding body. The pain, which was unbearable minutes ago, has transcended pain into something else. A total sensory overload, a white noise of neural signals that your fragmenting consciousness can barely process. Or perhaps the pain has stopped, because the neurons that process pain no longer exist as functional units. You're aware, dimly, that you're approaching the end. Not the singularity yet, that's still ahead, still in your future, measured in what might be seconds or might be longer, depending on the frame of reference. But the end of coherent existence, the point beyond which nothing that could be called you will exist, even in the loosest sense. Your last thought, if it can be called a thought, is something like wonder. Despite the agony, despite the horror, despite the absolute finality of what's happening, there's still some spark of amazement at the universe's strangeness, at the journey you've taken, at the impossibly extreme conditions you're experiencing. You came to understand, and you did understand, even if that understanding dies with you. The stretching continues. The particles that were you are now separated by distances larger than you ever were. And ahead, inexorable as fate, the singularity approaches, the final destination, the end of all journeys, the point where space-time itself reaches its limit. The singularity approaches where physics ends. You're being pulled towards something that shouldn't exist. The singularity, a point of infinite density, infinite curvature, infinite tidal forces, represents the ultimate boundary of physical reality. It's not just the end of your journey, but potentially the end of space-time itself, a place where all our equations break down, where all our theories fail, where mathematics produces infinities that signal its own inadequacy. The word singularity is mathematical in origin. It refers to points where functions become undefined, where calculations produce infinity or other nonsensical results. In the context of black holes, it describes a region where the curvature of space-time becomes infinite according to general relativity. But infinity is not a number you can measure or experience. Infinity is a concept, an abstraction, a mathematical way of saying bigger than any finite value you can name. What does infinite curvature actually mean? In gentler regions of space, curvature is the bending of space-time caused by mass and energy. Earth curves space-time slightly, creating what we experience as gravity. The sun curves it more. A neutron star curves it dramatically. A black hole curves it to the point where light cannot escape. And at the singularity, this curvature becomes so extreme that it breaks the coordinate system, that it exceeds any finite value, that it reaches mathematical infinity. But infinity cannot be physical reality. You cannot experience infinite density or infinite curvature because experience is finite. Something must happen before the true mathematical singularity. Some physics we don't yet understand must intervene. The question is, what? Quantum mechanics might provide the answer. In the quantum world, nothing can be compressed to a true point. The Heisenberg uncertainty principle forbids it. If you try to localize something to an infinitely small region, its momentum becomes infinitely uncertain, its energy becomes infinite, and the whole picture breaks down. Quantum mechanics abhors infinities as much as classical physics produces them. At scales approaching the Planck length, approximately 10 ho and 35 meters, unimaginably small, quantum effects on spacetime itself become important. At these scales, spacetime probably isn't smooth and continuous as general relativity assumes, but discrete and granular, perhaps made of tiny quantized units called Planck volumes. If this is true, then infinite compression is impossible. The singularity might be replaced by some quantum structure, some minimal size beyond which further compression cannot occur. String theory offers another perspective. If fundamental particles are not point-like but extended one-dimensional strings, then as you approach what classical theory calls the singularity, these strings might be stretched and deformed until they reach some limiting configuration. The theory makes different predictions in this regime, potentially avoiding the singularity altogether and replacing it with something exotic but finite, perhaps a region where strings transition to different vibrational modes, or where additional spatial dimensions become important. Loop quantum gravity, another approach to quantum gravity, suggests that spacetime is made of discrete loops or networks at the smallest scales. In this picture, infinite compression is impossible because you eventually reach the fundamental granularity of spacetime itself. The singularity might be replaced by a quantum bounce, a region where the geometry transitions from collapse to expansion, perhaps connecting our black hole to another universe or another region of spacetime. But these are all theoretical speculations, untested and perhaps untestable. No experiment can probe the singularity, no observation can reveal what happens there. It's hidden behind the event horizon, protected by cosmic censorship, forever beyond our ability to investigate directly. Every particle, every photon, every piece of information that reaches the singularity is trapped there, unable to report back to the external universe. From your perspective, rapidly approaching this enigmatic boundary, the physics is becoming increasingly extreme. The tidal forces have grown beyond catastrophic, beyond lethal, beyond any scale you can comprehend or survive. What remains of you, the dispersed atoms that were once organized into a human being, are being pulled into an ever tighter stream, a one-dimensional chain of particles approaching infinite density. The universe of your origin, the cosmos you spent your life in, is now completely inaccessible. Not just far away, but causally disconnected, existing in a past you cannot return to because returning would require travelling backward in time. The only reality that matters now is the immediate reality of falling, stretching, approaching the singularity that has become your inevitable future. If consciousness still exists in any form, and it almost certainly doesn't at this point, given the complete destruction of your neural structure, it would be experiencing something utterly beyond description. Not thoughts in any normal sense, but perhaps some final flickering of awareness, some last quantum of subjective experience before the final dissolution. You, or what was you, reach distances from the singularity measured in Planck lengths, the smallest distances that have meaning in quantum gravity. At this scale, spacetime itself becomes uncertain, fluctuating, probabilistic. The smooth geometry of general relativity gives way to quantum foam, a roiling sea of virtual black holes and wormholes appearing and disappearing at the Planck scale. The concept of time becomes ambiguous. In quantum mechanics, time and energy are conjugate variables related by uncertainty principles. At energies and densities this extreme, time itself might become indeterminate, spreading out into quantum superpositions. There might not be a definite moment when you reach the singularity, but rather a probabilistic smear of possible times, all equally real in some quantum sense. Space has similar ambiguities. The notion of specific positions breaks down when quantum uncertainty becomes comparable to the scales involved. You might be in multiple places simultaneously. In quantum superposition, your position undefined until something measures it. But there's nothing left to measure. No observer, no apparatus, just the fundamental quantum fields and whatever quantum gravity does at these scales. At energies this extreme, physics we've never observed comes into play. The strong nuclear force, the weak nuclear force, electromagnetism, and gravity, the four fundamental forces, might unify into a single force at Planck scale energies. This is the dream of a theory of everything, a single elegant description of all physical interactions. But we don't have this theory. We don't know if it exists or what form it takes. Some theories suggest that additional spatial dimensions become important at Planck scales. Our familiar 3 dimensions of space might be just a subset of a higher dimensional reality. As you approach the singularity, you might in some sense be entering these extra dimensions, experiencing geometry in 10 or 11 dimensions rather than the familiar 3 plus time. Other theories propose that the singularity might be a doorway to another universe. Some solutions to Einstein's equations, like the maximally extended Schwarzschild solution, describe geometries where the black hole interior connects to a white hole in another spacetime, a region from which matter and energy emerge. But these solutions are probably unphysical, requiring perfect symmetries that real black holes don't have. The white hole would be unstable, likely collapsing or being destroyed by quantum effects. Still others suggest the singularity might be a region where time itself ends, not in the sense of reaching a final moment, but in the sense that time ceases to be a meaningful concept. Just as the North Pole is the point where north becomes undefined, you can't go further north than the North Pole because north ceases to mean anything there. The singularity might be the point where future becomes undefined. There's no after the singularity because time itself terminates. In this view, reaching the singularity is not dying in the conventional sense, but ceasing to exist in a more profound way. You don't die, and then persist as a corpse. You stop being in space-time entirely. You're removed from the universe, erased from existence, not just killed, but uncreated in some fundamental sense. The atoms that were you reach the final Planck distance from whatever the singularity actually is. At this point, all descriptions fail completely. General relativity is broken down. Quantum mechanics is pushed beyond its limits. The combination, quantum gravity, remains a frontier of theoretical physics with no consensus solution. What happens in this final instant? Do the particles simply compress to infinite density, or does some quantum effect halt the collapse? Does information about what you were get preserved in quantum correlations, or is it genuinely lost? Does the singularity connect to another region of space-time, or is it a genuine boundary where reality ends? We don't know. We cannot know from outside the event horizon, and you, reaching this point, will not be able to tell us. If you could somehow experience this final moment, if some fragment of awareness could persist to witness the ultimate mystery, that experience would die with you. The knowledge would be forever trapped, forever hidden, forever beyond the reach of science. The singularity is the limit of human knowledge in the most absolute sense, not a limit we might overcome with better technology or cleverer theories, but a limit imposed by the structure of space-time itself. We can describe the approach mathematically. We can calculate trajectories, tidal forces, just time dilation. But the singularity itself remains forever beyond our reach, protected by an event horizon that ensures no information can escape to inform us what actually happens. In the final instant, if instant has meaning here, if time still exists in any recognizable form, the particles that will you encounter the singularity. What happens next is the greatest mystery in physics, and we'll never know the answer. The information paradox. Do you really die? Let's step back from the immediate experience of falling and consider a profound question that's troubled physicists for decades. What happens to information that falls into a black hole? This might seem abstract compared to the visceral horror of spaghettification, but it's actually about the most fundamental question we can ask. Do you, in some sense, survive? In physics, information has a technical meaning. It's the complete description of a system state at the quantum level, the positions, momenta, spins, and quantum numbers of every particle, plus all the correlations and entanglements between them. According to quantum mechanics, information cannot be created or destroyed, only transformed. If you know a system state now, you can calculate its state at any future time, and in principle, you can reconstruct its past states as well. This information conservation is fundamental to quantum mechanics. It's related to the unitarity of quantum evolution, the mathematical property ensuring that probabilities sum to 1, that total probability is conserved as systems evolve. If information were destroyed, unitarity would be violated. and the entire framework of quantum mechanics would need to be rebuilt. But black holes seem to destroy information. You fall in, carrying all the information that constitutes you, your memories, your physical structure, the quantum states of every particle in your body. You reach the singularity and are destroyed. Where does that information go? The naive answer is that it's trapped inside the black hole, hidden behind the event horizon but still existing in some form. This would preserve information, it's just inaccessible to external observers. But Stephen Hawking's discovery of black hole radiation complicated this picture dramatically. Hawking showed that black holes emit thermal radiation through quantum effects near the horizon. Virtual particle pairs, which normally appear and disappear throughout empty space, borrowing energy from quantum fluctuations, can become separated at the event horizon. One particle falls in while its partner escapes as Hawking radiation. The escaping particle is real, carrying energy away from the black hole. This radiation causes black holes to lose mass and eventually evaporate completely. A stellar mass black hole would take about 10⁻⁶7 years to evaporate, unimaginably longer than the current age of the universe. A supermassive black hole would take even longer. But in principle, eventually, the black hole disappears completely. Here's the problem. Hawking radiation appears to be perfectly thermal. Thermal radiation is random, carrying no information about its source. A lump of coal and a computer chip at the same temperature emit identical thermal radiation. If black holes emit only thermal Hawking radiation, then all the information about what fell in, all the information about you, is lost when the black hole finally evaporates. This creates a paradox. Quantum mechanics demands that information be conserved. Black hole evaporation appears to destroy it. Both cannot be true. Something must give, either quantum mechanics or our understanding of black holes, or both. This is the black hole information paradox, and it's one of the deepest problems in theoretical physics. Resolving it likely requires a complete theory of quantum gravity, unifying general relativity and quantum mechanics, which we don't yet have. But physicists have proposed several potential resolutions, each with profound implications. One possibility is that information is preserved in subtle correlations in the Hawking radiation. The radiation might not be perfectly thermal, but rather have tiny, incredibly subtle deviations that encode information about what fell in. These correlations would be exponentially difficult to detect. You'd need to collect nearly all the Hawking radiation a black hole ever emitted and perform impossibly precise quantum measurements, but they'd be there in principle, preserving unitarity. This solution is called black hole complementarity. It suggests that there are two complementary descriptions of what happens, both valid from different perspectives. From an external observer's viewpoint, you never really fall into the black hole. You're absorbed at the horizon, your information encoded in subtle patterns in the outgoing Hawking radiation. From your infalling perspective, you cross the horizon smoothly and continue to the singularity. Both descriptions are correct, but they describe the same events from different reference frames. The holographic principle provides another approach. It suggests that all the information in a black hole's interior is encoded on its two-dimensional event horizon, like a hologram. When you fall in, your three-dimensional information is projected onto the horizon's surface. The interior might just be one way of describing information that's fundamentally stored on the boundary. This leads to a radical conclusion. The interior of a black hole might not have independent physical existence. It might be an emergent phenomenon, a way of describing information stored on the horizon, not a separate region of space-time. Your journey to the singularity might be real from your perspective, but might be a derived description of information processes happening on the horizon's surface. The holographic principle extends beyond black holes to the entire universe. It suggests that our three-dimensional reality might be encoded on a two-dimensional surface, perhaps at the cosmological horizon, the boundary of the observable universe. We might be living in a cosmic hologram. Our three-dimensional experience is derived from information stored on a distant two-dimensional boundary. Another proposed resolution involves firewalls. This controversial idea suggests that the event horizon isn't smooth and unnoticeable as you cross it, but rather a violent, high-energy boundary, a firewall that would incinerate anything trying to cross. This preserves information because nothing really enters the black hole interior. Everything is destroyed at the horizon, with information preserved in the resulting radiation. But firewalls contradict general relativity's prediction that crossing the horizon should be smooth and uneventful. They require abandoning the equivalence principle, Einstein's insight that free fall is indistinguishable from floating in empty space, that there's nothing locally special about an event horizon. Most physicists resist this radical step, though it remains a possibility. ER-EPR is an even more radical proposal, suggested by Juan Maldacena and Leonard Susskind. It connects wormholes, Einstein-Rosen bridges, or ER, with quantum entanglement, Einstein-Podolsky-Rosen correlations, or EPR. The idea is that quantum entanglement between particles might be geometrically described by tiny wormholes connecting them through space. In this picture, when a particle falls into a black hole and becomes entangled with Hawking radiation, that entanglement is a wormhole connecting the interior to the exterior. Information isn't lost because it's connected via these quantum wormholes to the Hawking radiation. The interior and exterior are linked in a more fundamental way than we thought. This proposal blurs the distinction between quantum mechanics and geometry, suggesting they're different descriptions of the same underlying reality. It implies that space-time itself might emerge from patterns of quantum entanglement, that geometry is secondary to quantum information. String theory offers yet another perspective. In string theory, black holes can be modelled as bound states of fundamental strings and branes, higher dimensional objects. These models are exactly solvable in certain limits, and calculations show explicitly that information is preserved. The black hole's quantum state uniquely determines what went into forming it and what comes out as radiation. But these solvable models involve black holes in exotic spacetimes with extra dimensions, supersymmetry, and other features that real astrophysical black holes don't have. Whether the information preservation seen in these idealized models extends to realistic black holes remains unclear. Loop quantum gravity suggests that the singularity might be replaced by a quantum bounce, where the collapsing matter reaches some minimal size and then begins expanding again, possibly emerging into another region of space-time. If this is true, information might pass through the bounce, emerging in whatever region lies beyond, preserving unitarity in a global sense even if it's lost from our universe. The honest answer is that we don't know which, if any, of these proposals is correct. The black hole information paradox remains unsolved despite decades of brilliant work by the world's leading theoretical physicists. Every proposed solution has problems, requires assumptions we're not certain about, or leads to other paradoxes and puzzles. What this means for you, falling into the black hole, is deeply uncertain. Do you really die at the singularity, or does some version of you persist encoded in Hawking radiation? Does the information that constitutes you, your memories, your personality, your physical structure, survive in some form, or is it genuinely destroyed? If information is preserved through any of these mechanisms, then in some sense you survive, even if it's not a sense you'd recognize or find comforting. Your information might be encoded on the horizon, or preserved in correlations in Hawking radiation, or transmitted through a quantum bounce to another universe. Some pattern that captures what you were might persist, even if the organized, conscious living you is gone. But this isn't survival in any meaningful sense. You won't experience it. You won't be aware of existing as information encoded on a horizon or as correlations in thermal radiation. From your subjective perspective, you die at the singularity, or before it, from spaghettification, and that's the end. The information preservation that might occur doesn't help you, doesn't save you, doesn't offer an afterlife in any recognizable form, yet it matters philosophically and physically. If information is truly lost in black holes, then the entire framework of quantum mechanics needs revision. The paradox forces us to confront deep questions about the nature of reality, about the relationship between quantum mechanics and gravity, about what information really is, and whether it's truly fundamental to the universe. The paradox also highlights the limits of our current physics. We can describe black holes with general relativity, we can describe quantum mechanics, but we don't have a complete theory that unifies them, that works in the extreme conditions where both are important, at the singularity near the Planck scale, where quantum effects on spacetime itself become dominant. Solving the information paradox will require this unified theory, quantum gravity, which remains one of the greatest challenges in theoretical physics. String theory, loop quantum gravity, and other approaches make progress but haven't yet achieved consensus or experimental confirmation. So the question, do you really die, has no definite answer. Yes, in every sense that matters to subjective experience. Your consciousness ceases, your body is destroyed, your organized structure is obliterated. But maybe no, in some abstract informational sense, that preserves the pattern that was you in ways we don't fully understand. The black hole keeps its secrets, the singularity remains hidden. And the ultimate fate of information, and therefore of you, remains one of the cosmos's deepest mysteries. Hawking radiation, the black hole's quiet whisper. While you're falling toward your doom inside the black hole, something subtle and extraordinary is happening at the event horizon behind you. The black hole is glowing. Not with ordinary light, the glow is far too faint and too cold for human eyes to detect, but with what's called Hawking radiation, named after Stephen Hawking, who predicted it in 1974. This radiation represents one of the most profound discoveries in theoretical physics, connecting quantum mechanics, general relativity, and thermodynamics in unexpected ways. It revealed that black holes aren't entirely black, that they have temperature and entropy, that they can evaporate given enough time, and it created the information paradox we just discussed, forcing physicists to confront deep questions about the nature of reality. The mechanism behind Hawking radiation is subtle and quantum mechanical. In quantum field theory, what we call empty space, the vacuum, isn't truly empty. It seethes with quantum fluctuations, temporary violations of energy conservation permitted by Heisenberg's uncertainty principle. Virtual particle-antiparticle pairs constantly pop into existence throughout space, borrowing energy from quantum fluctuations, existing briefly, and then annihilating back into the vacuum before the energy debt must be repaid. In normal space, far from any black hole, these virtual pairs appear and disappear without consequence. They're fluctuations in the quantum fields, not real particles you could detect or interact with. But near a black hole's event horizon, something different can happen. When a virtual pair appears very close to the horizon, the intense gravitational field can separate them before they annihilate. One particle might fall across the horizon, while its partner escapes to infinity. The escaping particle is now real, no longer a virtual fluctuation but an actual particle carrying energy. This is Hawking radiation, but energy must be conserved. If a particle escapes carrying positive energy, where does that energy come from? The answer is that it comes from the black hole itself. The particle that fell in carries negative energy from the black hole's perspective. It reduces the black hole's total mass. The black hole has radiated energy, and in doing so, it has lost mass. This is how black holes evaporate. Slowly, incredibly slowly, they emit Hawking radiation and lose mass in the process. Eventually, given inconceivable amounts of time, they would evaporate completely, leaving only the radiation they emitted. The temperature of this radiation is inversely proportional to the black hole's mass. Larger black holes are colder. For a stellar mass black hole with 10 times the Sun's mass, the temperature is about 1/10,000,000th of a Kelvin, far colder than the cosmic microwave background radiation filling space. Such a black hole absorbs more energy from the universe than it emits through Hawking radiation, so it grows rather than shrinks. For Sagittarius A, the supermassive black hole you're falling into, the temperature is even lower, about 10 degrees or 14 Kelvin, 100 billionth of a Kelvin. At this temperature, the Hawking radiation is essentially undetectable, overwhelmed by other sources of radiation by many orders of magnitude. The black hole won't begin evaporating in earnest until the distant future, when the universe has expanded and cooled below even this infinitesimal temperature. But in principle, in the inconceivably distant future, Sagittarius A will evaporate. The process will accelerate as the black hole shrinks. Smaller black holes are hotter, so they radiate faster, which makes them shrink faster, which makes them hotter still. The final stages of evaporation would be rapid and violent, the last fragments of the black hole exploding in a burst of radiation. The total time for Sagittarius A to evaporate completely is approximately 10^99 years. To put this in perspective, the universe is currently about 10^10 years old. The last stars will burn out in about 10^14 years. Protons might decay, if they're unstable, in about 10^34 years. Even after all normal matter has decayed, after all stars have died, after the universe has become a thin soup of radiation and subatomic particles, black holes will persist, dominating the universe's mass-energy budget for timescales that dwarf all previous cosmic history. And then finally they too will evaporate, leaving behind only radiation in an eternally expanding universe. This is one possible ultimate fate of the cosmos, a universe of maximum entropy, thermal equilibrium, nothing left but diffuse radiation growing ever more dilute as space expands forever. Heat death, the final victory of entropy over order, the ultimate triumph of the second law of thermodynamics. But Hawking radiation is more than just a mechanism for black hole evaporation. It revealed that black holes are thermodynamic objects, governed by laws analogous to the laws of thermodynamics. They have temperature, which we've discussed. They also have entropy, a measure of disorder or hidden information. Black hole entropy is proportional to the area of the event horizon, not its volume as you might expect for normal objects. The formula, called the Bekenstein-Hawking entropy, shows that a black hole's entropy equals its horizon area measured in Planck areas divided by 4. This is enormous. Sagittarius A has entropy about 1091 times larger than the Sun's entropy, despite being only 4 million times more massive. This relationship between entropy and area led to the holographic principle we discussed earlier, the idea that all information in a volume of space can be encoded on its boundary. If black hole entropy really is proportional to horizon area, that suggests the information is stored on the surface rather than in the interior, like a hologram that encodes 3-dimensional information in 2 dimensions. The temperature and entropy of black holes also lead to laws resembling the laws of thermodynamics. The zeroth law of black hole mechanics says that horizon surface gravity is constant across the event horizon, analogous to temperature being constant in thermal equilibrium. The first law relates changes in mass, area, and angular momentum, analogous to the first law of thermodynamics relating energy, entropy, and work. The second law says horizon area can never decrease in classical physics, analogous to entropy never decreasing. Even a third law exists, analogous to the impossibility of reaching absolute zero temperature. These analogies were initially considered just that, analogies, mathematical curiosities without physical significance. But Hawking radiation revealed they're more than analogies. Black holes literally have temperature and entropy. The thermodynamic laws describe real physical properties. This was a profound discovery, suggesting deep connections between gravity, quantum mechanics, and thermodynamics that we're still working to fully understand. Hawking radiation also implies that black holes are not immortal. They're temporary structures that will eventually evaporate, leaving no permanent record of what fell in, unless information is somehow preserved in the radiation's correlations. This transforms our understanding of cosmic evolution. The universe's ultimate fate might not be dominated by black holes, but by their absence after they've all evaporated. From your perspective, falling toward the singularity, Hawking radiation is irrelevant. It's happening at the horizon behind you, emitted as you cross, but you'll never see or experience it. The radiation is too weak, too cold, utterly overwhelmed by other sources of energy and entropy. You might as well ignore it. It has no bearing on your fate. But from the external universe's perspective, Hawking radiation is the black hole's only communication with the outside world. Long after you've fallen in, long after you've been destroyed at the singularity, the black hole will continue emitting this faint glow, slowly bleeding away mass and energy, gradually shrinking over timescales longer than current cosmic age. If information about you is preserved in Hawking radiation's subtle correlations, then in some abstract sense, you'll be gradually emitted back into the universe over these vast timescales. The information that constituted you, scrambled beyond recognition, encoded in patterns of thermal radiation, might eventually escape, preserving unitarity even as it destroys any recognizable form of your identity. This is cold comfort. Whether your information is preserved or lost, you're dead. Your consciousness has ended. Your subjective experience has terminated. The information preservation physicists' debate is an abstract principle, important for fundamental physics, but meaningless to your lived experience. Yet Hawking radiation stands as one of the most beautiful achievements of theoretical physics, a prediction made purely through mathematical reasoning, connecting disparate areas of physics, revealing unexpected connections between gravity and quantum mechanics. It showed that black holes, far from being simple gravitational traps, are complex thermodynamic objects with rich physics we're still working to understand. As you continue your fall toward the singularity, the horizon above you glows with radiation you cannot see, announcing to the universe that something has fallen in, that mass energy has been added to the black hole, that the area has increased and with it the entropy. The universe's total entropy has grown, as it must, as the second law of thermodynamics demands, even as the organization that was you has been destroyed. In the cosmic ledger of entropy, you're being accounted for. Your death contributes to the universe's inexorable slide toward maximum disorder, toward heat death, toward the final state where no more work can be extracted, no more structure can be built, nothing remains but thin, cold, eternally dispersing radiation. The black hole glows faintly, the singularity beckons, and your journey approaches its end. What observers see? The eternal fall. Let's shift perspective dramatically. We've been experiencing the fall from your viewpoint, from inside the inertial reference frame plummeting toward the singularity. But what does someone outside the black hole see? What does an observer hovering at a safe distance watching your fall through a powerful telescope actually witness? The answer is strange, paradoxical, and beautifully illustrative of relativity's counterintuitive predictions. The external observer never sees you reach the event horizon. From their perspective, you never fall in. Your approach slows asymptotically, your image freezing at the boundary, preserved there for eternity. You become a ghost haunting the event horizon, visible but motionless, gradually fading but never disappearing completely. This is not an optical illusion or failure of observation. It's a consequence of the extreme gravitational time dilation near the horizon. As you fall closer, time for you passes more slowly relative to the distant observer. The effect grows without limit. At the horizon itself, time dilation becomes infinite. 1 second of your time corresponds to infinite time for them. Your crossing of the horizon exists infinitely far in their future. Let's trace this more carefully. Imagine your friend is hovering at a safe distance in a spacecraft, watching you fall with the best telescope technology can provide. At first, when you're far from the black hole, they see you falling normally, accelerating under gravity, moving faster and faster inward. Everything seems normal, relativistic effects are present but subtle. As you fall closer, they notice you're slowing down from their perspective. Not slowing in your own frame, you feel yourself falling faster and faster, accelerating relentlessly. But the light carrying your image to them is climbing out of an increasingly deep gravitational well, and time dilation is affecting the rate at which they see you move. You appear to them to be falling in slow motion. The effect intensifies dramatically as you approach the horizon. They see your movements become languorous, dreamlike. If you wave your hand, the motion takes longer and longer from their perspective. Your watch, if they can see it, appears to tick slower and slower compared to their own. Every process involving you, your motions, your biological processes, the oscillations of atoms in your body, appears to be running in slow motion from their viewpoint. The light from you is also changing. Photons climbing out of the gravitational well lose energy, their wavelength stretching, their frequencies decreasing. This gravitational redshift transforms the light your body emits. If you're illuminated by white light, they see you become reddish, then deep red, then infrared, then radio waves, the spectrum shifting steadily toward lower frequencies. Your image also dims. Fewer photons reach them per unit time as time dilation intensifies. The photons that do arrive are redshifted to lower energies, carrying less brightness. The combination makes you appear to fade gradually, growing dimmer and redder simultaneously, your image becoming increasingly difficult to detect. As you reach the horizon, from your perspective, crossing it smoothly in finite time, the external observer sees something different. Your approach slows to imperceptibility. Your image redshifts to infinite wavelength. You appear frozen just outside the horizon, a permanent ghost, neither crossing nor retreating, suspended in time. This frozen image persists, not for years or centuries, but forever, in principle. Long after you've crossed the horizon and died at the singularity from your own perspective, your image remains visible from outside, hovering at the edge, gradually fading but never completely vanishing. The photons carrying your final moments take longer and longer to climb out of the gravitational well, arriving at the distant observer over extended periods, creating an image that fades exponentially but never entirely disappears. In practice, the image becomes undetectable relatively quickly. The redshift becomes so extreme that photons shift to wavelengths measured in light years. The time dilation becomes so severe that individual photons arrive separated by years, then centuries, then millennia. The image dims below any possible detection threshold long before it vanishes completely. But in principle, with perfect detectors and infinite patience, the external observer could continue seeing your image indefinitely. This creates the bizarre situation where different observers experience fundamentally different realities. From your perspective, you cross the horizon in minutes or hours, continue falling, and reach the singularity shortly thereafter. From the external perspective, you never cross at all. You're frozen at the horizon forever. Both descriptions are equally valid. Neither is more true than the other. How can both be true? The resolution lies in understanding that now is not absolute. When you cross the horizon now from your perspective, that event doesn't correspond to any moment of now in the external observer's reference frame. It's infinitely far in their future. The event exists in space-time. It's a real point in the four-dimensional geometry, but it's not part of any time slice that the external observer considers to be the present. Think of it this way. Space-time is a four-dimensional structure containing all events, everything that happens anywhere, anytime. Different observers slice this four-dimensional structure into three-dimensional nows differently, like slicing a loaf of bread at different angles. Your crossing of the horizon is an event in space-time, a point in the four-dimensional geometry. But it's on a slice that the external observer would label infinitely far future, while you label it now. Both labels are correct from their respective viewpoints. This relativity of simultaneity is fundamental to special and general relativity. Events that are simultaneous for one observer are not simultaneous for another. Near a black hole, this effect becomes extreme to the point of seeming paradoxical. But it's the same principle that operates everywhere in relativity, just more dramatic. There are other effects the external observer would notice. If many objects fall into the black hole, not just you but gas, dust, other unfortunate travellers, they all appear to pile up at the horizon from the external viewpoint. The horizon should appear to be covered with frozen images of everything that ever fell in, layered like paintings on a canvas, each new layer added outside the previous ones. In reality, the images are so redshifted and dimmed that they're undetectable. But in principle, every particle that ever fell into the black hole since its formation remains visible at the horizon from the external perspective, creating a complete record of the black hole's entire history. This is related to the idea that information is encoded on the horizon. From the external viewpoint, nothing ever really goes inside, so information is preserved on the surface. The external observer would also see the black hole's horizon grow as you add your mass to it. The event horizon's size depends on the black hole's total mass. When you fall in, you add your mass, however small compared to the black hole's total mass, and the horizon expands slightly to accommodate the additional mass energy. From their perspective, the horizon grows to meet your frozen image, enveloping it, absorbing it into the black hole's structure. But this absorption happens asymptotically. The horizon approaches your frozen position, growing closer and closer but never quite reaching it in finite time from the external viewpoint. You and the horizon approach each other, both moving infinitely slowly from the observer's perspective, meeting only at the limit of infinite time. This creates a strange picture. From outside, the black hole is not a region of space-time with an interior but a surface, the event horizon, where matter and information accumulate, where everything that falls in becomes encoded in increasingly complex patterns on the two-dimensional boundary. The interior, from this perspective, might not have independent existence but be merely one way of describing the information on the surface. If multiple external observers watch your fall from different locations, different distances from the black hole, different angular positions, they would all agree on the essential features. They would all see you slow down, redshift, and freeze at the horizon. But the exact timing and details would differ depending on their motion and position. Each would have their own notion of simultaneity, their own way of slicing space-time into now and future. but all would agree that your crossing is infinitely far in the future from their perspective. Interestingly, if the external observer were to start falling toward the black hole themselves, accelerating inward to catch up with you, their observations would change. As they fall, they enter reference frames with stronger gravitational fields and different notions of simultaneity. From these new perspectives, you would appear to move faster, less frozen. If they fell fast enough, they might even see you cross the horizon before they do, experiencing your crossing as a past event relative to their own crossing. This illustrates again that whether you've crossed the horizon is not an absolute fact, but a frame-dependent statement. Different observers, depending on their motion and position, will disagree about whether you've crossed yet. All are correct from their own perspectives. The crossing is not a universal event that all observers can point to and say, "That happened then," but a relative event whose timing depends on the observer. For someone who jumps in after you, trying to catch up, they would see you ahead of them, falling toward the singularity. From their perspective, you did cross the horizon. They can see you inside, can watch your final moments before the singularity, but an observer who remains outside never sees this. The internal observer and external observer experience different realities, both valid, both consistent with the laws of physics. If the external observer waits long enough, impossibly long, longer than the current age of the universe many times over, they would eventually see the black hole begin to evaporate through Hawking radiation. The horizon would shrink slowly as mass energy is radiated away. Your frozen image at the horizon would be incorporated into this process somehow, your information either preserved in the radiation's correlations or lost depending on which resolution of the information paradox is correct. From the external observer's perspective, you never fall into the black hole in the traditional sense. You're absorbed by the horizon, your information encoded there, then gradually released as the black hole evaporates. The journey to the singularity that you experience is not part of their reality. It happens in a region of space-time infinitely far in their future, beyond the horizon of events they can observe or causally interact with. This disconnect between perspectives raises profound questions. Which description is more fundamental? The interior journey you experience or the surface encoding the external observer sees? Are these equally valid descriptions of the same reality, or is one more real than the other? The holographic principle suggests they're complementary, different ways of describing the same physical situation from different viewpoints. You falling to the singularity, and you being encoded on the horizon, are not contradictory, but complementary descriptions, like how quantum mechanics and classical mechanics describe the same physical world at different scales. But this complementarity comes at a cost, giving up the notion of a single objective reality independent of observers. Reality itself becomes observer-dependent, different for different reference frames, unified only in the four-dimensional space-time structure that contains all perspectives simultaneously. This is perhaps the deepest lesson of black holes, that reality is not absolute but relational, not objective but perspectival, not single but multiple. What happens depends on who's observing, where they are, how they're moving. Your death at the singularity and your eternal freezing at the horizon are both real, both true, both consequences of the same geometry viewed from different angles. The external observer watches your frozen image fade slowly into invisibility, red-shifted beyond detection, dimmed beyond observation. They know you're there in some sense, encoded on the horizon, or already destroyed at the singularity depending on perspective. But they can never know what you experienced, can never witness your crossing, can never see the interior or the singularity. Those remain forever hidden, protected by the event horizon, secrets the black hole keeps eternally. Your fall continues toward its conclusion, but from outside the fall appears to never end. Rotating black holes. The Kerr solution. We've been discussing a simplified scenario falling into a non-rotating black hole described by the Schwarzschild solution, but real black holes almost certainly rotate. They form from collapsing stars or merging black holes, processes that conserve angular momentum. A non-rotating black hole would be a special case, requiring exact cancellation of all rotation, which is unlikely to occur naturally. Rotating black holes are described by the Kerr solution, discovered by Roy Kerr in 1963. This solution is significantly more complex than the Schwarzschild solution, revealing exotic geometry and bizarre properties that non-rotating holes don't possess. If you were falling into a rotating black hole, which is more realistic, your experience would differ in important ways from what we've described. The most obvious difference is the ergosphere, a region outside the event horizon unique to rotating black holes. Within the ergosphere, spacetime itself is dragged along with the black hole's rotation so strongly that nothing can remain stationary, not even light. If you tried to hover in the ergosphere without orbiting, you'd be dragged along with the rotation whether you like it or not. It's as if you're caught in a cosmic whirlpool. Spacetime itself flowing around the black hole like water circling a drain. The ergosphere is not inside the event horizon. You can enter the ergosphere and escape again if you have sufficient velocity. But while you're there, you must move. Stationary observers cannot exist. This frame-dragging effect, also called the lens-thirring effect, exists around any rotating massive object, but becomes extreme near rotating black holes. Remarkably, the ergosphere enables a process called the Penrose process, named after Roger Penrose, who discovered it in 1969. An object entering the ergosphere can split into two parts, with one part falling into the black hole and the other escaping with more energy than the original object had. The escaping part has extracted energy from the black hole's rotation, slowing it down slightly. This is the only known way to extract energy from a black hole. Civilizations advanced enough might harness the Penrose process to extract vast amounts of energy from rotating black holes. A sufficiently advanced civilization could potentially extract up to 29% of a black hole's mass energy through this process, an energy source more efficient than nuclear fusion. This is pure speculation, but it's allowed by physics, making rotating black holes potential power sources for future civilizations. A rotating black hole has two event horizons, an outer horizon and an inner horizon, with the ergosphere surrounding the outer horizon. Between these horizons lies a region with even stranger properties than the normal black hole interior. The geometry admits closed, time-like curves, paths through space-time that loop back on themselves, allowing an object to return to its own past. These closed, time-like curves create all the paradoxes associated with time travel. Could you go back and prevent your own birth? Could you give yourself information you didn't have, creating causal loops with no beginning? The mathematics allows these curves, but whether they're physically possible remains debated. Quantum effects or cosmic censorship might prevent them from forming in realistic scenarios. Most physicists suspect that the region between the horizons is unstable. Quantum effects might cause it to collapse or create energy densities so extreme that the classical geometry breaks down. The inner horizon might be a place where classical general relativity fails completely, replaced by quantum gravity effects we don't yet understand. The singularity in a rotating black hole is not a point but a ring, a circle of infinite density and curvature surrounding the black hole's axis of rotation. Remarkably, the mathematics suggests you could pass through the center of this ring without encountering the singularity itself, potentially emerging into another region of spacetime. This other region is sometimes described as another universe, or a different part of our universe. The maximally extended Kerr solution, the complete geometry without truncation, contains infinite sequences of asymptotically flat regions, connected by black holes and white holes. You could potentially travel from our universe through the ring singularity into another universe, and from there through another black hole to yet another universe, ad infinitum. But this is almost certainly unphysical. The maximally extended solution requires perfect symmetry and ignores perturbations and quantum effects. Real rotating black holes probably don't contain traversable pathways to other universes. Small perturbations would destroy the delicate geometry. Quantum effects would create energy densities that prevent passage. The pathway, if it exists mathematically, almost certainly doesn't exist physically. Still, the mathematics is tantalizing. It suggests that general relativity admits solutions where black holes serve as portals to other regions of spacetime. Even if these particular solutions are unphysical, they hint that the geometry of spacetime might be far richer and more connected than we typically imagine. If you were falling into a rotating black hole, the rotation would affect your trajectory in noticeable ways. You'd be pulled along with the rotation, gaining angular momentum even if you initially approached radially. The frame dragging would twist your path into a spiral. Depending on your initial trajectory and the black hole's rotation rate, You might orbit several times before crossing the horizon, caught in the rotating space-time like water circling a drain. The maximum rotation rate for a black hole is limited. If a black hole rotates too fast, the event horizon disappears and the singularity becomes naked, visible to the outside universe. This naked singularity would violate cosmic censorship, the principle that singularities should always be hidden behind horizons. Most physicists believe nature prevents the formation of naked singularities through some mechanism, possibly quantum effects or the behavior of matter approaching extreme rotation. Sagittarius A, the black hole you're falling into in our scenario, probably rotates at a significant fraction of the maximum rate. Observations of its surrounding gas and the orbits of nearby stars suggest moderate to high rotation. If you're falling into the real Sagittarius A, frame dragging would affect your fall, spiraling you around the black hole's axis, potentially flinging you outward if your trajectory is just right, or pulling you inevitably inward if it's not. The visual experience of falling into a rotating black hole would differ from a non-rotating one. The distortions of starlight would be asymmetric, twisted by the rotation. The shadow would be slightly offset and distorted rather than perfectly circular. The accretion disk, if present, would show complex patterns of light and dark caused by the rotating spacetime's effects on photon trajectories. Inside the outer horizon of a rotating black hole, the geometry becomes even stranger than in a non-rotating hole. There's a region where closed time-like curves exist, where you could, in principle, travel backward in time. But this region is probably unstable, collapsing or becoming quantum-dominated before you could exploit it for time travel. The inner horizon, if it exists stably, is a Cauchy horizon, a boundary beyond which determinism breaks down. Outside the Cauchy horizon, knowing the state of the universe now determines its future uniquely. Beyond the Cauchy horizon, the past doesn't uniquely determine the future. Multiple different futures become possible from identical starting conditions. This is disturbing from a physics perspective and might indicate that the inner horizon is unphysical, destroyed by quantum effects before you could reach it. Approaching the ring's singularity, tidal forces would still destroy you, though the pattern of destruction would differ from a non-rotating hole. Instead of being stretched into a one-dimensional strand, you'd be pulled toward the ring from all directions perpendicular to it. The forces would still be fatal, still infinite at the singularity itself, still beyond anything material structure could withstand. Whether you could actually pass through the ring without encountering infinite tidal forces is unclear. The classical mathematics allows it, but classical mathematics is almost certainly wrong at these scales. Quantum effects, which we cannot yet properly calculate, probably dominate. The ring singularity might be replaced by some quantum structure, or the tidal forces might remain finite but lethal, or passage might simply be impossible for reasons we don't understand. The rotating black hole remains one of the most exotic objects general relativity predicts. It's a place where time travel might be possible, where connections to other universes might exist, where space-time exhibits behaviors that seem like science fiction but follow rigorously from Einstein's equations. Whether these mathematical possibilities correspond to physical realities we may never know. Cosmic censorship and the event horizon ensure that the most exotic regions remain forever hidden from external observation. But they add richness to our picture of black holes, revealing that these objects are far more complex than simple gravitational traps. They're structures with internal geography, with multiple horizons and exotic regions, with properties that push physics to its absolute limits and beyond. They're laboratories for testing our deepest theories, even if we can never directly observe or visit those laboratories. As you fall, spiraling now in the rotating space-time twisted by frame dragging, pulled inexorably toward the ring singularity, you might wonder what lies beyond. Could the ring truly be a portal to another universe? Will you emerge somewhere else, or will you simply be destroyed by tidal forces or quantum effects at the singularity? The answer remains one of the cosmos's deepest mysteries, hidden forever behind the event horizon's veil. Quantum mechanics at the horizon. As you approach the event horizon, quantum mechanics, which has been lurking in the background of our discussion, becomes increasingly important. We've mostly treated your fall using classical general relativity, which describes space-time as a smooth, continuous geometry. But at small scales and extreme conditions, quantum effects dominate, and the classical picture breaks down. Near the event horizon, quantum mechanics reveals phenomena that classical physics misses entirely. The most important is Hawking radiation, which we've discussed, but there are other quantum effects that change our understanding of what the horizon is and what happens there. In quantum field theory, the vacuum is not empty, but filled with quantum fluctuations. Virtual particles appear and disappear constantly, borrowing energy from the vacuum's zero-point energy for brief moments allowed by the uncertainty principle. These fluctuations are normally undetectable. They occur at such small scales and for such brief times that they have no macroscopic consequences. But near a black hole horizon, these quantum fluctuations become important. The intense gravitational field can separate virtual particle pairs before they annihilate, as we described for Hawking radiation. But there are other effects too. The vacuum near the horizon is fundamentally different from the vacuum far away, in ways that quantum mechanics makes precise. From the perspective of quantum field theory, what you perceive as empty space depends on your motion and position. An observer at rest far from the black hole and an observer falling through the horizon disagree about what constitutes the vacuum state, the state of minimum energy with no particles present. What one observer calls vacuum, the other might observe as containing particles. This is called the Unruh effect, closely related to Hawking radiation. For an accelerating observer in flat space-time, far from any gravitational field, the vacuum appears to contain a bath of thermal radiation proportional to their acceleration. The faster you accelerate, the hotter the radiation you observe, even though inertial observers see nothing. This seems bizarre, but it's a rigorous prediction of quantum field theory in curved or accelerated reference frames. Near a black hole, you're in an accelerating reference frame because the intense gravity creates acceleration. From your perspective falling freely, you might see quantum effects that external observers don't, or vice versa. The horizon itself, from certain perspectives, might appear to glow with quantum radiation, though exactly how this appears is subtle and depends on the observer's trajectory. This observer dependence of particles is unsettling. We usually think of particles as objective things that either exist or don't, but quantum field theory in curved space-time shows that particle content is observer-dependent. Different observers performing particle measurements on the same quantum state might get different answers, and both answers would be correct from their perspectives. This relates to the black hole information paradox. If what constitutes a particle depends on the observer, then the notion of information being carried by particles becomes ambiguous. Information that seems to be lost from one perspective might be preserved from another. The resolution of the information paradox likely involves carefully tracking how information transforms between different observer perspectives, accounting for these quantum effects. Another quantum effect near the horizon involves entanglement. When a virtual pair separates at the horizon, one particle escaping as Hawking radiation, the other falling in, the two particles are quantum entangled. They're correlated in ways that persist regardless of spatial separation. Measuring the state of one particle instantly affects the state of the other, even though they're separated by the event horizon. This entanglement between interior and exterior particles is crucial for the ERPR proposal we mentioned earlier. The idea that quantum entanglement might be geometrically described by wormholes connecting the entangled particles. If correct, this would mean the black hole interior and exterior are connected by a network of quantum wormholes, providing a mechanism for information to escape through quantum channels even though classical communication is impossible. The horizon itself might not be as well defined in quantum mechanics as in classical relativity. In classical general relativity, the horizon is a precise surface, the boundary of the region from which light cannot escape. But quantum mechanics introduces uncertainty. The horizon's position might fluctuate quantum mechanically, blurring over a small region rather than being a precise boundary. These quantum fluctuations of the horizon are tiny, on the order of the Planck length, about 10⁻³ meters. They're utterly negligible for macroscopic objects like you, but they might be important for understanding what happens to information and for resolving the information paradox. If the horizon fluctuates, then information that classically falls behind it might quantum mechanically remain accessible, encoded in these fluctuations. The firewall proposal we mentioned earlier is a radical suggestion that quantum effects might dramatically change the horizon's character. According to some interpretations of quantum mechanics applied to black holes, the horizon might not be a smooth, empty region, but a violent, high-energy boundary, a firewall that would incinerate anything trying to cross. The firewall argument goes like this. Hawking radiation escaping the black hole must be entangled with radiation emitted earlier to preserve information, but the escaping radiation must also be entangled with its partner that fell behind the horizon to maintain the quantum state of the vacuum near the horizon. A quantum system cannot be maximally entangled with two different systems simultaneously. This violates quantum monogamy of entanglement. Something must give. One resolution is that the entanglement behind the horizon is broken, which requires enormous energy concentration at the horizon, a firewall. If this is correct, you'd be incinerated before crossing the horizon, never experiencing the smooth crossing general relativity predicts. But this requires abandoning the equivalence principle, the idea that free fall is locally indistinguishable from floating in empty space, which is foundational to general relativity. Most physicists resist the firewall idea because it's so radical, but it remains a possibility. It highlights how quantum mechanics and general relativity create tensions we don't fully understand, especially in extreme environments like black hole horizons. The resolution might require new physics, some synthesis of quantum mechanics and gravity that we haven't yet achieved. Another quantum consideration is whether the singularity itself exists in quantum gravity. Classical general relativity predicts singularities, points of infinite density and curvature. But quantum mechanics abhors infinities. The uncertainty principle prevents compressing anything to a true point. At Planck scales, quantum effects on spacetime geometry should become dominant. String theory, loop quantum gravity, and other quantum gravity approaches suggest that singularities might be replaced by quantum structures. Perhaps the singularity is not a point, but a Planck scale region where spacetime becomes discrete, or where strings reach their tension limits. Perhaps collapse is halted at some minimal size, creating a quantum bounce that might connect to another region of spacetime. These are speculations, but they suggest that the classical singularity, with its infinite densities and curvatures, might not be the final answer. Quantum gravity, whatever form it takes, likely modifies the extreme interior of black holes in ways that avoid true infinities. But we don't know the details because we don't have a complete, experimentally confirmed theory of quantum gravity. From your perspective falling toward the singularity, quantum effects are becoming increasingly important. At some point, probably at Planck scales within about 10 and 35 meters of the classical singularity, quantum gravity effects dominate and classical general relativity fails. What happens then is unknown. The quantum state of spacetime itself becomes important, and we don't have the mathematics to describe it properly. You might imagine that quantum mechanics would make your death less certain, that quantum superposition might mean you both hit the singularity and don't hit it simultaneously, that quantum many-worlds might split reality into branches where you survive. But this is probably wishful thinking. Quantum mechanics changes the details of what happens at Planck scales, but it doesn't prevent tidal forces from tearing you apart, doesn't provide miraculous escape from the singularity's gravitational well. The quantum state of what was you, the particles that made up your body, now dispersed into a stream falling toward the Planck scale core, is highly entangled, quantum correlated in complex ways. This quantum information might be preserved somehow, might eventually emerge in Hawking radiation, might be encoded on the horizon. But this doesn't help you subjectively. Your consciousness has ended. Your macroscopic structure has been destroyed. The quantum information is just that, information, without the organization that made it you. Quantum mechanics adds subtlety and complexity to the black hole picture, but doesn't fundamentally change your fate. You fall, you're destroyed by tidal forces. You reach the singularity or whatever quantum structure replaces it, and you die. The quantum details of how information is preserved or where it goes might matter for fundamental physics, but they don't change the subjective reality of falling into a black hole. As you approach the Planck scale core, quantum effects explode in importance. Classical spacetime dissolves into quantum foam, geometry becomes uncertain, causality becomes probabilistic, and our ability to describe what happens evaporates along with classical reality. The singularity, or whatever replaces it in quantum gravity, awaits, and physics, pushed to its absolute limits, has no more to tell us. Time and causality, inside the horizon. Inside the event horizon, time behaves in ways that seem impossible, violating everything your intuition tells you about causality and the flow of time. We've mentioned that the radial direction becomes time-like, but what does this really mean for your experience? What does it mean to live in a place where space has become time? Normally, time is the dimension you move through involuntarily at a fixed rate, 1 second per second, always forward, never backward. Space consists of 3 dimensions you can move through freely: forward and back, left and right, up and down. You choose where to go in space, but you have no choice about moving forward in time. Inside the horizon, one spatial direction, the radial direction toward the singularity, exchanges properties with time. It becomes a dimension you move through involuntarily at a fixed rate, always inward, never outward. Just as you cannot stop moving forward in time, you cannot stop moving inward toward the singularity. Just as you cannot move backward in time to yesterday, you cannot move outward away from the singularity. This creates a profound change in causality, the relationship between causes and effects, between past and future. Outside the horizon, causes can propagate in any spatial direction. Light spreads outward in all directions from a source. Effects can reach distant locations. The future is open. Many different outcomes are possible from any given present state. Inside the horizon, causality becomes directional in a new way. All causes, all effects, all influences propagate toward the singularity. Light emitted in any direction ultimately moves inward. Information cannot travel outward. The future is not open but fixed. There is only one possible future, and it's at the singularity. Every causal chain, every sequence of events, every trajectory through space-time leads to the same place. This creates something like fatalism, but it's geometric fatalism, not philosophical fatalism. It's not that you're destined to reach the singularity by some mystical force or predetermined plan. It's that the geometry of space-time itself makes all paths lead there. It's not fate, but physics. The singularity is in your future in the same way tomorrow is in your future, inevitable because of how time works, not because of any mysterious destiny. But what does this mean experientially? How would you experience living in a space where one direction has become time? The honest answer is that it's almost impossible to imagine. Our intuitions about space and time are built from our experience in normal space-time, where time is one-dimensional and uniform, where space is three-dimensional and navigable. We have no experience with spaces where these properties change. You might try to turn around, to point yourself outward, to try to move away from the singularity. But turning around doesn't help because outward is not a direction in space you can move in. It's a direction in time. Specifically, it's toward your past. Trying to move outward is like trying to move into yesterday. You can point in that direction, can imagine going there, but you cannot actually travel there because the geometry forbids it. Every action you take, every force you apply, every movement you make results in continued inward motion. If you fire a rocket, the thrust might change your transverse motion. You might move sideways or rotationally, but it cannot stop your inward fall. You continue toward the singularity regardless of what you do. All roads lead to the same destination. This is radically different from being in a strong gravitational field outside the horizon. There, gravity is strong and escape might be impossible practically, requiring more energy than you have, but the geometry still permits outward paths in principle. With enough energy, with a powerful enough rocket, you could escape. Inside the horizon, no amount of energy helps. Outward paths don't exist. The geometry has changed fundamentally, closing off entire categories of motion. The light cones, regions of space-time that light can reach from any given point, have tipped over inside the horizon. Outside, light cones point primarily into the future but spread out spatially, allowing light to reach distant locations. At the horizon, light cones tip so that their edges become tangent to the horizon. Light trying to escape can at most hover at constant radius, neither escaping nor falling in. Inside, light cones tip completely, pointing inward toward the singularity. All directions light can travel lead to the singularity. Since nothing moves faster than light, and light must move toward the singularity, everything must move toward the singularity. You cannot go where light cannot reach. Your possible futures are constrained by the light cones, and those light cones all terminate at the singularity. The singularity is not a place you might reach, but a time you will reach. From a four-dimensional space-time perspective, the interior of the black hole is a region where all time-like geodesics, paths that objects in free fall follow, converge on the singularity. The geometry is such that these paths cannot avoid it, cannot loop around it, cannot terminate anywhere else. The singularity is a boundary of space-time in the time direction, analogous to how the Big Bang is a boundary in the past-time direction. This raises philosophical questions about free will and determinism. Outside the black hole, you have free will in the sense that multiple different futures are compatible with the laws of physics. You can choose to go left or right, to act or not act, and different choices lead to different futures. But inside the black hole, your future is uniquely determined. You will reach the singularity, period. Does this eliminate free will? The answer depends on what you mean by free will. If free will requires multiple possible futures, then yes, you lose it inside the horizon. There's only one possible future. But if free will is about the ability to make choices that influence your path, then you retain it. You can still choose your actions, even if all actions lead to the same ultimate destination. You can choose how you spend your remaining time, even if you cannot choose to have unlimited time remaining. This is similar to the situation all of us face regarding death. We will all die eventually, there's no escaping it, no choice that avoids it. Does this eliminate free will? Most people would say no. We still have meaningful choices about how we live even though death is inevitable. Inside the black hole, the singularity plays a role similar to death. Inevitable, approaching, unavoidable, but you still have agency about how you respond to it. Causality also becomes strange in other ways. In a rotating black hole, there might be closed time-like curves, paths through space-time that loop back on themselves, allowing you to return to your own past. These create causal paradoxes. Could you prevent yourself from entering the loop? Could you give yourself information you didn't have, creating a causal loop with no beginning? Most physicists suspect these closed time-like curves are unphysical, that quantum effects or other mechanisms prevent them. But their existence in the classical mathematics shows that general relativity permits time travel in principle, that the geometry of space-time can be configured to allow closed causal loops. Whether nature actually allows this, or whether some cosmic censorship prevents it, remains uncertain. Another strange feature of the interior is the behavior of particle world lines, the paths particles take through space-time. Outside the black hole, world lines extend into the indefinite future. Particles continue existing, moving through space, experiencing time. Inside the black hole, world lines terminate at the singularity. Particles don't continue existing indefinitely, but reach an endpoint, a boundary where their world lines end and they cease to exist in space-time. This termination is unlike anything in normal physics. Particles can be created or destroyed by converting to from energy, but they don't simply end. Their world lines don't terminate without cause, but at the singularity, they do terminate, not because of any interaction or process, but because space-time itself ends, because there's no beyond for the world line to continue into. From your perspective, experiencing this strange interior, time marches forward as always, 1 second per second, moment following moment. But the content of those moments is bizarre. Every moment brings you closer to the singularity, not in the sense of moving through space, but in the sense of advancing through time. The singularity is your future, approaching as inevitably as tomorrow. You cannot stop time. You cannot pause it, reverse it, escape it. And inside the black hole, you cannot stop your approach to the singularity for the same reason. It's temporal, not spatial. The singularity is not a place you're traveling to, but a time you're living toward. And time, inside the black hole as outside, moves forward relentlessly, carrying you toward endings you cannot avoid. The geometry has spoken, the singularity awaits, and time, that familiar one-way flow, has become your enemy, carrying you inexorably toward dissolution, beyond the black hole. Wormholes and white holes. Throughout our journey, we've treated the black hole as a one-way trip to oblivion. You fall in, you reach the singularity, you cease to exist. but some solutions to Einstein's equations suggest more exotic possibilities. What if the black hole is not an ending but a transition? What if there's something beyond the singularity? Or what if the black hole connects to somewhere else entirely? The most famous exotic possibility is the wormhole, a hypothetical tunnel through space-time connecting two distant regions. The idea emerged from the mathematics of black holes themselves. When Einstein and Nathan Rosen studied the Schwarzschild solution in 1935, they discovered that the equations described not just a black hole, but a connection between two regions of space-time, an Einstein-Rosen bridge. In the simplest version, this bridge connects two universes or two distant parts of one universe. You enter through a black hole in one location and potentially emerge through a white hole, a time-reverse black hole that expels matter rather than consuming it, in another location. You'd traverse the wormhole, travelling from one mouth to the other, potentially covering vast distances instantaneously. It sounds like science fiction, and indeed, most science fiction wormholes are based on this concept, but the mathematics is rigorous, following directly from general relativity. The equations permit these structures. The question is whether they can exist physically, or whether they're merely mathematical curiosities that nature never actually produces. The problem with classical wormholes is that they're unstable. The Einstein-Rosen bridge in its original form collapses so quickly that nothing can traverse it. Light entering one end would be crushed by the collapsing geometry before reaching the other end. To make a traversable wormhole, one you could actually travel through, you need something to hold it open against the tendency to collapse. That something is exotic matter, matter with negative energy density, violating the usual energy conditions that normal matter obeys. In quantum field theory, negative energy is possible in special circumstances related to the Casimir effect and squeezed quantum states. But whether you can accumulate enough negative energy to stabilize a macroscopic wormhole remains unknown and seems unlikely. Even if stable wormholes exist, they probably don't form naturally from black holes. The maximally extended Schwarzschild solution, the complete geometry containing both black and white hole regions, requires perfect symmetry that would be destroyed by any perturbation. A real black hole, formed from collapsing matter or merging black holes, wouldn't have this symmetry. The wormhole connection, if it exists mathematically, would be severed by the asymmetry, leaving just a black hole with a singularity. White holes are even more problematic. These are time-reversed black holes, regions that expel matter rather than consuming it, with horizons that can be exited but not entered. They appear in some solutions to Einstein's equations but are probably unphysical. A white hole would violate the second law of thermodynamics by decreasing entropy. Small perturbations would probably cause it to collapse into a black hole immediately. Some cosmologists have speculated that the Big Bang might be a white hole, a singularity from which our entire universe emerged. This is an intriguing idea, potentially explaining the universe's origin, but it creates more problems than it solves and lacks supporting evidence. From your perspective falling through the black hole, you're not experiencing any exotic wormhole or white hole geometry. You're falling toward the singularity, being torn apart by tidal forces, approaching the end of your journey. If wormholes exist, they're not accessible through realistic black holes formed by collapsing stars or accreting gas. You're not going to emerge in another universe or another part of this one. You're going to die. But let's imagine, counterfactually, that you did fall through a traversable wormhole. What would you experience? The journey would be brief. Wormholes in general relativity are typically very short, even if they connect distant regions. You might pass through a throat, a narrow region connecting the two mouths, experiencing intense tidal forces, though presumably survivable if the wormhole is traversable. Emerging from the other end, you'd see a new region of space-time. If it's another universe, the laws of physics might be different values of fundamental constants, different particle species, different dimensionality of space. If it's a distant part of our universe, you'd see different stars, different galaxies, a completely different view of the cosmos. Time travel through wormholes is theoretically possible under certain conditions. If the two mouths of a wormhole are in relative motion, or in different gravitational fields, they might connect different times as well as different locations. You could enter one mouth in the present and emerge from the other in the past or future. This creates the usual time travel paradoxes, which most physicists suspect nature prevents through mechanisms like quantum effects or topology censorship. Some theorists have proposed that microscopic wormholes might exist constantly, appearing and disappearing at the Planck scale as part of spacetime's quantum foam. These quantum wormholes would be far too small for anything macroscopic to traverse, but they might play a role in quantum gravity, possibly even providing a mechanism for quantum entanglement at a distance through the ER-EPR correspondence we discussed. The Kerr solution for rotating black holes contains even more exotic geometry, including ring singularities you might pass through without hitting them. Mathematical extensions of this solution describe multiple universes connected through the black hole interior, with both black hole and white hole regions allowing entry and exit. But again, these are probably mathematical artifacts rather than physical realities. Some researchers have explored whether black holes might be connected to other regions of space-time through quantum effects rather than classical wormholes. The holographic principle and ER-EPR suggest deep connections between black holes and distant regions, mediated by quantum entanglement. Perhaps what looks like a journey to the singularity from a classical perspective is actually a transition to another region, when quantum effects are properly included. Loop quantum gravity offers another possibility. In this approach, the singularity might be replaced by a quantum bounce, where the collapsing matter reaches a minimum size and then begins expanding again. This expansion could potentially lead to the birth of a new universe on the other side of the bounce, a baby universe budding off from ours through the black hole. Our entire universe might have originated this way, born from a black hole in another universe. These ideas are highly speculative. We have no observational evidence for wormholes, white holes, baby universes, or connections through black holes to other regions of space-time. They're theoretically possible in certain interpretations of general relativity and quantum gravity, but possibility doesn't imply actuality. Nature might not utilize all the exotic solutions that mathematics permits. From a practical standpoint, you falling into Sagittarius A would not experience any of these exotic phenomena. You'd experience what general relativity predicts for realistic black holes: spaghettification, approach to the singularity, and death. The wormholes and white holes, if they exist at all, are not accessible through the black holes we observe, but the mathematics of these exotic structures teaches us something important: that spacetime is far stranger and richer than our everyday experience suggests. The geometry permits connections that seem impossible, paths that seem paradoxical, structures that defy intuition. Even if these particular solutions are unphysical, they hint that spacetime might have a complexity we're only beginning to appreciate. As you continue your fall toward the singularity, the exotic possibilities fade into academic curiosity. There is no tunnel to another universe waiting for you, no white hole to emerge from, no shortcut through spacetime. Just the relentless geometry pulling you inward, the tidal forces tearing you apart, the singularity approaching as inevitably as time itself. The black hole keeps its secrets. If there's something beyond, you'll never be able to tell anyone. The event horizon ensures that all discoveries made inside remain forever hidden, forever lost to science, forever beyond our reach. The singularity approaches, and whatever lies beyond, if anything lies beyond, remains the cosmos's most profound mystery. The cosmic context: black holes in the universe. Let's zoom out from your personal fall and consider black holes in their cosmic context. They're not isolated curiosities, but integral components of the universe's structure and evolution. Understanding their role helps us appreciate both their individual strangeness and their collective significance. Black holes exist throughout the universe in staggering numbers. Our Milky Way galaxy alone contains perhaps 100 million stellar mass black holes, remnants of massive stars that exploded as supernovae. These are scattered throughout the galaxy, invisible except when they accrete matter from nearby companions, creating X-ray binaries that telescope can detect. Most of these stellar black holes are isolated, drifting through the galaxy, interacting with nothing, completely dark and undetectable. You could pass relatively close to one, within light years, and never know it was there unless its gravity perturbed your trajectory. They're cosmic ghosts, remnants of dead stars, persisting indefinitely until the universe's end. Then there are the supermassive black holes, like Sagittarius A that you're falling into. These lurk at the centres of most galaxies, with masses ranging from millions to tens of billions of times the Sun's mass. Nearly every galaxy with a substantial bulge contains a central supermassive black hole. Their origin remains partly mysterious. How did they grow so large so quickly in the early universe? Possible formation mechanisms include direct collapse of massive gas clouds in the early universe, or gradual growth through mergers and accretion over billions of years. Some might have formed from the remnants of the first generation of stars, which were far more massive than modern stars. However they formed, supermassive black holes appear to be fundamental components of galaxy formation and evolution. The relationship between supermassive black holes and their host galaxies is intimate and puzzling. The mass of the central black hole correlates tightly with properties of the surrounding galaxy, particularly the velocity dispersion of stars in the galactic bulge. Somehow, black holes that occupy tiny fractions of their galaxy's volumes influence the structure of the entire galaxy. This connection suggests feedback mechanisms. When supermassive black holes accrete matter actively, becoming quasars or active galactic nuclei, they release enormous energy, sometimes more luminous than the entire rest of their galaxy. This energy can heat and expel gas from the galaxy, regulating star formation. The black hole and galaxy co-evolve, each influencing the other's growth. Quasars, the extremely luminous active galaxies powered by supermassive black holes, were far more common in the early universe. Looking at distant galaxies, looking back in time due to light's finite speed, astronomers see many quasars. In the modern universe, most supermassive black holes are quiescent like Sagittarius A, accreting matter slowly if at all, quiet compared to their violent youth. Between stellar mass black holes, up to tens of solar masses, and supermassive black holes, millions to billions of solar masses, there might exist intermediate mass black holes, with masses of hundreds to thousands of suns. Evidence for these is tentative. Some ultra-compact dwarf galaxies might contain them, and some X-ray sources suggest their presence, but we lack definitive confirmation. Black holes also exist as binary systems, orbiting each other, spiraling inward over time through gravitational wave emission, eventually merging in catastrophic collisions. These mergers, detected by LIGO and Virgo gravitational wave observatories starting in 2015, release more energy in seconds than the Sun will emit in its entire 10 billion year lifetime. Gravitational waves from black hole mergers provide a new way to observe these objects. Traditional astronomy uses electromagnetic radiation, light in various forms, but black holes don't emit light. Gravitational waves, ripples in space-time itself, allow us to hear black holes collide, measuring their masses, spins, and orbital parameters. This gravitational wave astronomy is revolutionizing our understanding. The mergers detected so far involve stellar mass black holes, but future space-based detectors like LISA, Laser Interferometer Space Antenna, will observe supermassive black hole mergers. When galaxies collide, a common occurrence over cosmic timescales, their central supermassive black holes eventually merge, creating gravitational wave signals visible across the universe. Black holes also affect their surroundings through jets. When accreting matter, black holes can launch jets of plasma traveling near light speed, extending sometimes for millions of light years. These jets, powered by the black hole's rotation and magnetic fields threaded through the accretion disk, pump enormous energy into the surrounding space, affecting galaxy evolution and the intergalactic medium. The formation of stellar mass black holes from massive stars is relatively well understood. Stars above about 25 solar masses end their lives in core collapse supernovae. If the core exceeds the Tolman-Oppenheimer-Volkoff limit, the maximum mass a neutron star can support, it collapses directly to a black hole. Some stars might collapse without producing visible supernovae, forming black holes quietly through failed supernovae. The most massive stars might undergo pair instability supernovae, where gamma-ray photons convert to electron-positron pairs, causing runaway collapse. These explosions completely destroy the star, leaving no remnant, no black hole, no neutron star, nothing. This creates a mass gap, where black holes of certain masses should be rare or absent, a prediction partially confirmed by observations though with puzzling exceptions. Black holes might have formed in the early universe through different mechanisms. Primordial black holes could have condensed from density fluctuations shortly after the Big Bang before stars existed. These could have any mass, from microscopic to supermassive. Some physicists speculate that primordial black holes might constitute some or all of dark matter, the mysterious substance comprising 85% of the universe's matter, but invisible to telescopes. Detecting primordial black holes is challenging. Microscopic ones would evaporate quickly through Hawking radiation, possibly contributing to gamma-ray backgrounds. Larger ones would be invisible except through their gravitational effects, microlensing events where they pass in front of distant stars, temporarily brightening them, or gravitational wave signals from mergers. Current evidence neither confirms nor rules out significant populations of primordial black holes. Black holes play a role in cosmic evolution, extending beyond their local effects. They're sinks for matter and information, removing complexity from the universe, increasing entropy. Over immensely long timescales, far exceeding the current cosmic age, black holes will dominate the universe's matter content. After stars burn out, planets disintegrate, and protons decay, if they do, black holes will be the last massive objects remaining. Eventually, even black holes evaporate through Hawking radiation. The smallest evaporate first, the largest last. The final supermassive black holes might persist for 10-100 years, an incomprehensibly long time before finally evaporating. After that, the universe contains only radiation and elementary particles, spreading ever thinner as space expands, approaching thermal equilibrium, heat death. The final state where no more work can be extracted, no more structure can form. This far future dominated by black holes seems bleak, but it's just one possible scenario based on current physics. Future discoveries might reveal new physics that changes the picture. Perhaps dark energy evolves, changing the universe's expansion rate. Perhaps quantum effects prevent true heat death. Perhaps something we don't yet understand intervenes. The far future is speculation built on extrapolation from current knowledge. From your perspective falling into Sagittarius A, these cosmic considerations seem remote. You're facing immediate personal dissolution, not the universe's fate in 10-100 years. But your fall is connected to these larger patterns. You're becoming part of a supermassive black hole that has shaped its galaxy's evolution for billions of years. Your mass, however infinitesimal, contributes to its growth. Your information, if preserved in Hawking radiation, will eventually be released over timescales beyond comprehension. Black holes are not just bizarre physics labs or theoretical curiosities. They're fundamental players in the cosmic drama, shaping galaxies, regulating star formation, creating the most extreme environments in the universe, and possibly connecting to the universe's ultimate fate. Understanding them is essential to understanding cosmology, galaxy evolution, stellar death, and the nature of space-time itself. As you fall, your personal tragedy playing out over minutes or hours, you're participating in processes that operate over cosmic timescales, contributing infinitesimally to a black hole that has existed for billions of years and will persist for billions more. Your individual story ends, but the black hole continues, patient and inexorable, accumulating mass, growing slowly, shaping its galaxy, awaiting the distant future when it too will evaporate into the void. The universe is vast, old, and strange. Black holes are among its strangest denizens, objects so extreme they break our intuitions, so massive they warp space-time into impossible geometries, so patient they outlast stars and galaxies and perhaps everything else. You're falling into one, experiencing firsthand what billions of years of cosmic evolution have created. It's terrifying, it's awe-inspiring, and it's ending. The singularity approaches, the universe watches, impassive. And your journey nears its conclusion, the mathematics of doom. Throughout this journey, we've avoided detailed mathematics, translating the equations of general relativity into experiences and images. But the mathematics is beautiful, elegant, and worth at least glimpsing. The equations that describe your fall are among the most profound achievements of human thought. Einstein's field equations, relating the geometry of spacetime to its matter-energy content. Einstein's field equations are deceptively compact. In their simplest form, they can be written as a single line relating the Einstein tensor, describing spacetime curvature, to the stress-energy tensor, describing matter and energy. But this single line unpacks into 10 coupled nonlinear partial differential equations, notoriously difficult to solve except in highly symmetric situations. The Schwarzschild solution, describing a non-rotating black hole, was found by Carl Schwarzschild in 1916, just months after Einstein published general relativity. Schwarzschild was serving in the German army during World War I, calculating artillery trajectories by day and solving Einstein's equations by night. He found the exact solution for the space-time geometry around a spherically symmetric mass, then sent it to Einstein, who was astonished that someone had solved his equations so quickly. The Schwarzschild solution reveals the metric, the mathematical object describing distances and intervals in space-time. The metric tells you how to measure distances between nearby points, how to calculate the proper time along a world line, how to determine whether paths are time-like, slower than light, space-like, would require faster than light travel, or null, light-like. For a non-rotating black hole, the metric has a particularly elegant form in Schwarzschild coordinates. But these coordinates have a problem. They become singular at the event horizon, with some terms becoming infinite. This led to decades of confusion about whether the horizon was a physical singularity or just a coordinate artifact. The resolution came from finding better coordinate systems. Eddington-Finkelstein coordinates, developed in the 1920s and 1950s, removed the coordinate singularity at the horizon, showing that infalling observers cross smoothly without encountering anything special. Kruskal-Shekaras coordinates, developed in the 1960s, cover the entire spacetime including the interior and exterior, revealing the full geometry. These coordinate transformations are more than mathematical tricks. They reveal physical truth. The horizon is not a physical barrier, but a coordinate artifact in Schwarzschild coordinates, a place where those particular coordinates fail, not where spacetime itself has a problem. Different coordinates reveal the horizon's true nature as a null surface, a one-way membrane in spacetime. The geodesic equation describes how particles move through curved spacetime. It's the relativistic generalization of Newton's law of inertia. Objects follow straight lines in spacetime unless acted upon by forces, but straight line means something subtle in curved space. A geodesic, the path of extremal, usually minimal, proper time or proper distance. Solving the geodesic equation for your trajectory through the black hole's geometry yields precise predictions. Your acceleration, your velocity, the time remaining until you reach the singularity, all can be calculated from the metric and your initial conditions. The mathematics is deterministic and precise, even though the physics at the singularity itself remains mysterious. The curvature of spacetime is measured by the Riemann tensor, a mathematical object with 20 independent components in four-dimensional spacetime. The Riemann tensor encodes how spacetime is bent, how geodesics converge or diverge, how vectors change when parallel transported around loops. It's the fundamental descriptor of gravity in general relativity. From the Riemann tensor, we can derive the Ricci tensor and Ricci scalar, which appear in Einstein's field equations. We can also derive the Kretschmann scalar, a measure of curvature invariant under coordinate transformations. The Kretschmann scalar approaches infinity at the singularity, confirming that it's a genuine singularity, not a coordinate artifact like the horizon. The Penrose diagram is a way to visualize the entire spacetime geometry of a black hole, compressing infinite regions into finite drawings. These diagrams use conformal transformations that preserve angles but not distances, allowing the entire past and future of the spacetime to be shown on a single page. Penrose diagrams reveal the causal structure, which events can influence which other events, more clearly than other representations. On a Penrose diagram for a Schwarzschild black hole, the singularity appears as a horizontal line at the top, representing all of space at the final moment of time for infalling objects. The event horizon is diagonal lines, actually null surfaces, separating the interior from the exterior. Radial light rays travel at 45-degree angles. Time-like world lines, like yours, are more vertical. The diagram makes clear that all time-like paths in the interior end at the singularity. There's no escaping it geometrically. For rotating black holes, the Kerr solution adds complexity. The metric now depends on both radius and angle, reflecting the rotation's axial symmetry. There are two horizons, an ergosphere, and the ring singularity. The complete Kerr geometry admits closed time-like curves, wormholes, and other exotic features, though their physical reality remains questionable. The mathematics also describes tidal forces, the differences in gravitational acceleration across extended objects. These are measured by the equation of geodesic deviation, which quantifies how nearby geodesics converge or diverge. Near a black hole, geodesics converge radially, pulling you longer, and diverge tangentially, squeezing you thinner, creating the spaghettification effect. The magnitude of tidal forces at any location depends on the second derivative of the gravitational potential, how quickly gravity changes as you move through space. Near the singularity, this second derivative approaches infinity, creating infinite tidal forces that no material can withstand. The mathematics predicts your inevitable destruction with brutal precision. Hawking's derivation of black hole radiation required combining general relativity with quantum field theory, a partial union of these usually incompatible frameworks. The calculation involves analysing quantum field behaviour in curved spacetime, a subtle enterprise requiring careful treatment of what constitutes vacuum, particles, and energy in different reference frames. The result? That black holes have temperature inversely proportional to their mass and emit thermal radiation at that temperature is one of theoretical physics' most remarkable achievements. It connects gravity, quantum mechanics, thermodynamics, and information theory in ways that weren't anticipated, revealing deep relationships between seemingly disparate areas of physics. The black hole entropy formula, relating entropy to horizon area rather than volume, suggests that information in a volume is bounded by the area of its boundary. This holographic principle, if correct, implies that physics in 3 spatial dimensions might be equivalent to physics on a 2-dimensional boundary, a profound insight about the nature of reality itself. These mathematical structures, metrics, tensors, equations, diagrams, are not mere descriptions of physical reality. In general relativity, they are physical reality at the most fundamental level we can access. Space-time is not a stage where physics happens, but is itself a dynamical physical entity, described by these mathematical objects, evolving according to Einstein's equations. Your fall through the black hole is described by a world line, a curve in 4-dimensional space-time connecting events in your history. This world line has a definite length measured in proper time, the time you experience along the path. The proper time from crossing the horizon to reaching the singularity is finite and calculable. For Sagittarius A's, it's hours or perhaps a day, depending on your trajectory. The mathematics is certain even where the physics is murky. We can calculate your trajectory precisely using general relativity, right up until the Planck scale near the singularity where quantum effects presumably dominate. The equations predict your fate with mathematical rigour, even though we don't understand the physical details of what happens at the singularity itself. This is both the power and the limitation of mathematical physics. The equations give precise predictions about observables, what you'd measure, what you'd experience, how long until various events. But they don't explain why space-time has this geometry, don't reveal what the singularity is, don't tell us whether the mathematical structures correspond to something more fundamental. Mathematics describes but doesn't explain. It predicts but doesn't enlighten. The equations of general relativity are phenomenally successful at describing gravity and curved space-time, but they're effective theories, approximations to some deeper reality, presumably involving quantum gravity, that we don't yet understand. As you approach the singularity, the mathematics that has faithfully described your journey breaks down. The curvature becomes infinite. The equations produce nonsensical results. The geometry becomes singular, undefined, impossible to extend further. The mathematics has reached its limits, along with your life. Beyond this point, we need new mathematics, new physics, new insights we don't yet possess. The singularity is not just the end of your journey, but the end of general relativity's ability to describe space-time. What happens next requires physics we're still searching for. The equations fall silent, the singularity awaits, and mathematics, having brought us to the edge, can take us no further. The final moments. This is it, the end. You're approaching the singularity, or whatever quantum structure replaces it, and these are your final moments. What was you? The thoughts, memories, consciousness, the organised pattern of matter that made you human, is almost entirely gone. What remains is a dispersed stream of particles, a one-dimensional chain of matter falling in formation, carrying no structure, no information, no trace of what it once was. Consciousness ended some time ago. The neural tissue that generated subjective experience has been torn apart by tidal forces, neurons separated by distances too great for signaling, synapses severed, networks destroyed. There is no thinking happening, no awareness, no experiencing of these final moments. What we describe is not experienced but inferred. What would be happening to the particles that were you if we could somehow observe from an impossible vantage point? The tidal forces have reached unimaginable magnitudes. The difference in gravitational acceleration between the front and back of what was once your body, now stretched across kilometers, exceeds the strength of any material by factors of millions or billions. Every structure has failed. Every molecule has been pulled apart. Every atomic bond has been stressed beyond its limit. You exist now only as individual atoms, and even those are being challenged. The electromagnetic forces holding electrons to nuclei are powerful, but gravity near the singularity is approaching levels where even these forces might be overcome. Atoms might be ionized, electrons stripped away, leaving nuclei and free electrons in a plasma more extreme than anything in the observable universe except perhaps the Big Bang's first instance. The stream of particles that was you is contracting transversely while elongating radially. You're becoming thinner and thinner in 2 dimensions while stretching ever longer in the radial direction. The cross-sectional area approaches zero. The length approaches infinity. You're becoming truly one-dimensional, a mathematical line rather than a physical object. Time itself is becoming ambiguous. At these extreme curvatures, quantum effects on space-time structure should dominate. Time might not be a smooth, continuous flow, but granular, discrete, jumping in Planck time intervals of about 10 Hz to 43 seconds. The very concept of moment might break down, replaced by quantum superpositions of different space-time geometries. Space might also be granular at these scales. The Planck length, about 10 or Herschel 35 meters, is thought to be the smallest distance with physical meaning. Below this scale, quantum fluctuations of space-time geometry become so violent that the notion of distance loses meaning. The smooth space-time of general relativity dissolves into quantum foam, a seething uncertainty where geometry itself fluctuates. As the stream of particles approaches within Planck distances of the singularity, all our theories fail completely. General relativity has produced infinities, infinite curvature, infinite density, infinite tidal forces, which signal the theory's breakdown. Quantum mechanics is needed, but standard quantum mechanics assumes a fixed space-time background, which doesn't exist here. We need quantum gravity, a theory we don't yet have. Different approaches to quantum gravity make different predictions about what happens. String theory suggests the singularity might be replaced by a Planck scale structure, where strings reach their maximum tension. Loop quantum gravity suggests a quantum bounce where collapse reverses into expansion. Other theories propose different resolutions. Without experimental evidence, we cannot determine which, if any, is correct. One possibility is that the classical singularity really exists, a point, or ring, of infinite density where space-time genuinely ends, where all world lines terminate, where physical reality ceases. In this scenario, you simply stop existing at the singularity, not dying in the usual sense of transitioning from living to dead, but ceasing to exist entirely, removed from space-time, annihilated in the most complete sense possible. Another possibility is that quantum effects prevent true infinities, replacing the singularity with some Planck-scale quantum structure. Perhaps space-time has a minimal volume, quantum grains that cannot be compressed further. Perhaps collapse is halted at Planck scales by quantum pressure effects. Perhaps the geometry transitions to something exotic, extra dimensions, different topologies, connections to other regions of space-time. If loop quantum gravity is correct, the quantum bounce might reverse the collapse. The particles that were you might begin expanding again, emerging perhaps into another region of space-time, possibly even another universe. This is wildly speculative, but the mathematics of loop quantum gravity admits such scenarios. Whether nature implements them remains unknown. The information that constituted you is approaching its ultimate fate. If information is truly preserved, it must be encoded somehow in the quantum state of the black hole and eventually emerge in Hawking radiation. But how information about your specific arrangement of particles, your specific quantum state, could be preserved through spaghettification and apparent destruction, the singularity remains mysterious. Perhaps information is preserved holographically on the event horizon, as the holographic principle suggests. Perhaps it's encoded in quantum entanglement between interior and exterior particles. Perhaps it's scattered across the Hawking radiation in correlations too subtle to ever recover in practice, but present in principle. Or perhaps our understanding of information is incomplete, and quantum gravity will reveal new principles governing information in extreme conditions. From a four-dimensional spacetime perspective, the singularity is a boundary, a place where world lines end, where spacetime terminates. It's like the edge of a map beyond which no territory exists. You reach this boundary and simply cannot go further because there is no further to go. Time ends, space ends, existence ends. The geometry admits no extension beyond the singularity. But this might be an artifact of classical general relativity. Quantum gravity might eliminate the boundary, replacing it with something smoother, a transition rather than a termination. The world lines that classically end might quantum mechanically continue in some form, though not in a way we can currently calculate or visualize. In the final Planck time before the singularity, 10 rounds of 43 seconds, an interval so brief that light travels only 1035 meters, quantum effects explode in importance. The geometry becomes quantum, a superposition of different curvatures. Causality becomes probabilistic rather than deterministic. The notions of space, time, before, after, here, there, all dissolve into quantum uncertainty. What happens in this final instant? We don't know. The mathematics stops working. The physics becomes speculative. We can imagine possibilities but cannot calculate probabilities, cannot make predictions, cannot say with confidence what actually occurs. The singularity guards its secrets absolutely. One thing is certain. From the perspective of the external universe, none of this matters observationally. Whatever happens to you at the singularity happens behind the event horizon, forever hidden from outside observers. No information about your fate, no details of the singularity's structure, no resolution of the questions we've posed can escape to inform science. The event horizon ensures that the black hole's interior remains forever beyond our reach. If you could somehow think in this final moment, if consciousness could persist through the complete destruction of neural structures, if awareness could exist as disembodied information in quantum states, what would you experience? The convergence of all light to a single point ahead? The dissolution of spacetime geometry into quantum foam? The sensation of time ending, of reaching the final moment beyond which no moments exist? These questions are probably meaningless. Consciousness requires structure, patterns of information processing, organized matter maintaining gradients far from equilibrium. None of this exists at the singularity. You're not experiencing anything because the substrate for experience has been destroyed. The questions we're asking are like asking what a computer experiences when it's disassembled into individual atoms. The question presumes something that doesn't exist. The particles reach the singularity. The world lines terminate. The journey ends. Whether this is a genuine ending or a transition to something beyond, we cannot say. The singularity is the final mystery, the ultimate unknown, the place where all our knowledge fails and all our theories break down. What happens at the singularity is the deepest question in physics, and we may never know the answer. Not because we lack the intelligence or the tools, but because the universe itself might forbid us from knowing. The event horizon is nature's ultimate censorship, ensuring that whatever happens at the singularity remains forever hidden, forever unknowable, forever beyond the reach of science. The journey is complete. The fall is finished. And you, whatever you were, whatever information constituted your existence, have reached the end, or perhaps a beginning, or perhaps an ending and a beginning are the same thing in quantum gravity. Or perhaps the question itself is meaningless. The singularity keeps its secrets, and you, having fallen into the black hole, have become one of those secrets, hidden forever behind the event horizon, lost to the universe, dissolved into mystery. Implications and insights. Having completed this thought experiment journey from distant space to the singularity, having experienced what falling into a black hole would be like from multiple perspectives, we must step back and consider what we've learned. Not just about black holes specifically, but about physics, reality, knowledge, and the limits of human understanding. The first and most obvious lesson is humility. Black holes reveal how little we truly understand about the universe at fundamental levels. We have theories, general relativity, quantum mechanics, that work phenomenally well in their domains. But where these domains overlap, in the extreme conditions near singularities, our theories break down. We don't have quantum gravity. We don't know what happens at singularities. We cannot resolve the information paradox with certainty. This ignorance is not temporary, not a matter of needing more time or better instruments. It's structural. The event horizon prevents us from observing the interior. Even if someone falls in and discovers the answers, they cannot communicate them to the outside universe. Black holes create regions of spacetime that are fundamentally inaccessible to science, forever beyond the reach of experiment and observation. This raises profound questions about the limits of knowledge. Are there truths about the universe that we cannot know, not because we lack the intelligence, but because the structure of reality itself prevents access? The interior of black holes might be such a realm, knowable to those who fall in but forever unknowable to science, which requires reproducible observations and testable predictions. The second lesson concerns the nature of reality itself. Our journey has revealed that reality is not absolute but perspectival, not objective but observer-dependent. From your perspective falling in, you cross the event horizon and reach the singularity in finite time. From an external observer's perspective, you never cross, you freeze at the horizon forever. Both descriptions are equally valid. Neither is more true than the other. This observer dependence extends beyond time to the very content of reality. Whether you've crossed the horizon is not a universal fact but a frame-dependent statement. Whether particles exist depends on the observer's motion. Whether information is preserved depends on which resolution of the information paradox is correct. Reality itself seems to be relational rather than absolute. This is uncomfortable for human intuition. We want to believe in objective reality, a single truth about what exists, what happens when events occur. But relativity and quantum mechanics both suggest reality is more subtle. Different observers experience different realities, all consistent with the laws of physics, unified only in the four-dimensional space-time structure that accommodates all perspectives simultaneously. The third lesson is about the relationship between mathematics and physical reality. Throughout our journey, mathematics has guided us, describing your trajectory, predicting your experiences, revealing features of space-time geometry. The mathematics is precise, elegant, beautiful. But it's also limited. At the singularity, it produces infinities and breaks down. The mathematical structures we use are approximations to deeper reality, effective theories valid in certain regimes but failing at extremes. This raises the question, is mathematics discovering reality or inventing it? Do mathematical structures exist independently, with physics being the study of which structures correspond to physical reality? Or is mathematics a human invention, a language we've created that happens to describe nature effectively in accessible regimes? The success of mathematics in physics is so profound it seems unlikely to be coincidental. Yet we don't understand why mathematics works so well. The fourth lesson concerns information and entropy. The black hole information paradox reveals tensions between quantum mechanics and general relativity that we haven't resolved. If information is truly fundamental, if the universe's quantum state evolves unitarily, preserving information, then black holes must preserve it somehow. But how? When matter falls in and appears to be destroyed at the singularity, the resolution likely involves recognizing that information can be encoded in unexpected ways, on boundaries rather than in volumes, in correlations rather than in particles, in quantum entanglement rather than in classical states. The holographic principle suggests that reality might be holographic, with information in volumes encoded on boundaries. If true, this revolutionizes our understanding of space, information, and reality itself. The fifth lesson is about cosmic censorship and the protection of causality. The singularity is hidden behind the event horizon, prevented from affecting the external universe, unable to send signals or influence events outside. This cosmic censorship might be nature's way of protecting causality from the paradoxes and inconsistencies that naked singularities would create. If singularities were visible, if we could observe them directly, We might see regions where physics breaks down, where time travel is possible, where causality is violated. By hiding singularities behind horizons, nature preserves the consistency of physics in the observable universe. We can do physics, can make predictions, can understand the universe because the most extreme regions are quarantined, isolated, prevented from contaminating the regime where our theories work. The sixth lesson concerns the relationship between gravity and thermodynamics. Black holes have temperature, entropy, and obey laws analogous to thermodynamics. This connection runs deep. It's not coincidental or metaphorical, but reflects fundamental relationships between gravity, quantum mechanics, and information. Gravity, it seems, is not just geometry but also thermodynamics. Space might emerge from more fundamental quantum information. This has led to revolutionary ideas like the holographic principle and gauge gravity duality, suggesting that gravity in some spacetimes is equivalent to quantum field theory on their boundaries. These dualities hint at a deeper structure, that different-looking theories might be different descriptions of the same underlying reality, like how the same object casts different shadows from different angles. The seventh lesson is about time itself. Our journey has shown time behaving in bizarre ways, slowing near horizons, becoming a spatial dimension inside them, possibly ending at singularities. Time is not the absolute background Newton imagined, but a dynamic feature of space-time, affected by matter and energy, flowing at different rates in different places, possibly granular at Planck scales rather than continuous. This fluidity of time challenges our deepest intuitions. We experience time as universal and uniform, flowing at 1 second per second, the same for everyone. But this is an illusion of living in weak gravitational fields and moving at non-relativistic speeds. Near black holes, time's true nature is revealed. Flexible, observer-dependent, convertible to and from spatial dimensions under extreme conditions. The eighth lesson concerns the limits of reductionism. Physics has been remarkably successful by reducing complex phenomena to simpler components and fundamental laws. But black holes suggest this reductionism has limits. The holographic principle implies that the interior of a black hole might not have independent existence but be derivable from information on the horizon. The whole is not just the sum of parts, but might be describable entirely by boundary data. This hints that space-time itself might be emergent rather than fundamental, arising from more basic quantum information, not existing as an independent substrate. If true, this would mean that space, time, and gravity are not fundamental but derived, emergent from quantum entanglement patterns or other informational structures we're only beginning to understand. The ninth lesson is about the cosmic future. Black holes dominate the universe's far future, persisting after stars burn out, gradually accumulating matter, eventually evaporating through Hawking radiation over timescales that dwarf current cosmic age. Understanding black holes means understanding the universe's ultimate fate, the slow slide toward maximum entropy, heat death, the final state where no structure remains and no work can be done. This fate seems bleak, but it's based on current physics extrapolated over unimaginable timescales. New physics discovered in the future might change the picture, or life and intelligence might find ways to persist even in this hostile far future, extracting energy from black hole evaporation or from other exotic sources. The far future is speculation, but black holes will certainly play a central role. The 10th and final lesson is about the power and limits of thought experiments. Our entire journey has been imaginary. You didn't actually fall into a black hole, and no human ever will. Yet through careful reasoning based on established physics, through imagining experiences and working through their implications, we've learned genuine truths about black holes, relativity, quantum mechanics, and reality itself. This is the power of thought experiments in physics. Einstein developed special and general relativity partly through thought experiments, imagining riding on light beams, standing in accelerating elevators, watching clocks in motion. These imaginary scenarios, carefully analysed, revealed truths about reality that experiments later confirmed. Our thought experiment falls in this tradition, using imagination disciplined by physics to explore regions we cannot physically access. But thought experiments have limits. They can reveal what our theories predict, but not whether those predictions are correct when they extend beyond observation. Our description of the singularity is based on general relativity, But we know general relativity fails there. The true singularity might be completely different from what we've described. Thought experiments guided by incomplete theories lead to incomplete conclusions. Putting these lessons together, black holes emerge as more than exotic astronomical objects. They're laboratories for fundamental physics, testing grounds for our deepest theories, challenges to our understanding of space, time, causality, information, and reality itself. They reveal the universe at its most extreme, where the laws of physics are pushed to breaking points, where new physics must emerge to resolve paradoxes and inconsistencies. Your imaginary fall has taken us on a journey through modern physics, general relativity, quantum mechanics, thermodynamics, information theory, cosmology. We've encountered unsolved problems, unresolved paradoxes, and fundamental mysteries. We've learned both what we know and what we don't know, both where our theories succeed and where they fail. The black hole keeps its secrets. The singularity remains hidden. The information paradox stays unsolved. But by imagining your fall, by thinking carefully through what would happen, we've glimpsed truths about reality that observation alone could never reveal. We've pushed human understanding to its limits and found those limits to be both frustrating and fascinating. The journey ends. The thought experiment concludes, but the questions remain, waiting for future generations of physicists to solve, waiting for new theories to emerge, waiting for the next revolution in our understanding of space, time, and the cosmos. The black hole is patient, it will wait, standing at the edge of mystery. We return now from our impossible journey. You have not really fallen into a black hole. You're safe, wherever you are, whatever you're doing as you experience this. The journey was imaginary, a thought experiment, a way of exploring physics through the medium of narrative and experience. But the physics was real. The predictions were genuine. The mysteries we encountered are actual unsolved problems that physicists grapple with today. What have we learned by taking this journey together? The nature of reality. Perhaps the deepest lesson is that reality is stranger than we ever imagined. The universe revealed by modern physics, relativistic, quantum, governed by curved space-time and probability amplitudes, bears little resemblance to the universe of common sense. Time is not absolute, space is not fixed, matter is not solid, causality is not simple. Black holes concentrate these strangeness into singular objects that defy intuition at every turn. They're places where time stops and starts again in different guises, where space becomes time, where what happens depends on who's observing, where information might be encoded in surfaces rather than volumes, where the very fabric of reality reaches its limits and tears. Our everyday intuitions, honed by evolution to navigate Earth's surface at human speeds and scales, are worthless here. Common sense fails completely. Intuition provides no guidance. We must rely on mathematics, pure abstract reasoning, to navigate these extreme territories. And even mathematics eventually fails at the singularity, producing infinities that signal its own inadequacy. This should inspire both humility and wonder. Humility because we're forced to recognize how limited our intuitions are. How much of reality operates according to principles we never would have guessed without careful observation and mathematical reasoning. Wonder because the universe is so much richer and stranger than we had any right to expect. The power of physics. Yet within this strangeness, physics provides genuine understanding. General relativity, despite being a century old, successfully predicts black hole behavior in stunning detail. The orbit of Mercury, gravitational lensing, gravitational waves, or black hole shadows, all predicted by Einstein's theory, all subsequently confirmed by observation. The theory works, describing reality with precision and elegance. Quantum mechanics, equally strange and counterintuitive, has been verified to incredible precision in countless experiments. It describes atomic behavior, semiconductor physics, chemical bonds, and presumably quantum fields near black hole horizons. It works, even though we struggle to understand what it means, even though interpretation remains debated. The fact that we can describe black holes at all, that we can predict what falling into one would be like, that we can calculate trajectories and time dilations and tidal forces, testifies to physics' power. We're describing objects so extreme they should be beyond our comprehension, using theories developed by thinking about far gentler phenomena. Yet the theories work, extrapolating successfully to these extremes. This is remarkable and worth celebrating. We live in an age where we can understand the universe's most extreme environments, where mathematics and physics can take us to places we can never physically visit, where human reason can grasp the cosmos from its smallest quantum scales to its largest cosmological expanses. This is an extraordinary achievement of human intellect, the limits of knowledge. But our journey has also revealed limits, both practical and fundamental, to what we can know. The practical limit is observational. We cannot see inside black holes. The event horizon hides the interior forever. No information can escape to inform us what happens there. We can theorize, can extrapolate from known physics, can imagine scenarios, but we cannot observe, measure, or test our ideas directly. The fundamental limit is deeper. Some truths about the universe might be forever beyond our reach, not because we lack instruments or intelligence, but because the structure of reality itself prevents access. The interior of black holes represents such a realm. The singularity holds secrets that might be knowable to those who reach it, but cannot be communicated to the outside universe. This is philosophically profound. We're accustomed to thinking that patient investigation will eventually reveal all truths, that no question is permanently unanswerable, but black holes suggest otherwise. Some regions of space-time are fundamentally inaccessible to science. Some questions have answers, but answers that can never be verified, never be tested, never be incorporated into the body of scientific knowledge. This doesn't mean we should give up or become pessimistic. It means we should recognize that knowledge has boundaries, that science has domains where it works and domains where it cannot reach. This recognition itself is valuable. Understanding the limits of understanding is a kind of meta-knowledge that helps us navigate the world more wisely. The unfinished symphony. Our journey has also revealed that physics is unfinished, spectacularly successful in many domains but incomplete, with holes and tensions that need resolution. The conflict between general relativity and quantum mechanics, most acute at black hole singularities, demands resolution. We need quantum gravity, a theory unifying these frameworks, but we don't yet have one. The information paradox remains unsolved despite decades of brilliant work. Does information fall into black holes and get destroyed, violating quantum mechanics? Or is it preserved somehow through mechanisms we don't fully understand? Different physicists favour different resolutions, but no consensus has emerged. The holographic principle hints at revolutionary insights about the nature of space and information, but we don't understand it completely. String theory and loop quantum gravity offer approaches to quantum gravity, but remain unverified experimentally. The far future of the cosmos, dominated by evaporating black holes, is speculation based on extrapolations we cannot test. These gaps and uncertainties are not failures but opportunities. They're where the next revolutions in physics will happen, where new Einstein-level insights might emerge, where our understanding of reality might transform as dramatically as it did with relativity and quantum mechanics. The unfinished nature of physics is exciting. There's still so much to discover, so many mysteries to solve, so many opportunities for future generations to make breakthrough discoveries. The human element. Throughout this journey, we've oscillated between the personal and the cosmic, between your individual experience falling and the universe-scale implications of black holes. This oscillation is intentional. It reflects how physics works, connecting the intimate and immediate to the vast and abstract. You, falling toward your death, experience time slowing, light distorting, forces pulling. These are immediate, visceral, personal realities, but explaining them requires invoking curved space-time, gravitational fields, reference frames, abstract concepts that transcend any individual experience. Physics bridges these scales, connecting the personal to the universal. This is part of physics' beauty. It takes subjective experience, what you see, what you feel, and reveals objective truth beneath. The distorted starlight reflects space-time curvature. The tidal forces demonstrate gravity gradients. Your experience, however unique, follows universal laws that apply everywhere, everywhen to everyone. Yet physics also reminds us of our smallness. You're a pattern of atoms, a temporary configuration of matter, subject to forces vastly more powerful than yourself. The black hole cares nothing for your hopes, fears, consciousness, or dreams. It operates according to impersonal laws, crushing you not through malice but through geometry. You're not special to the universe. You're just particles following geodesics through curved space-time. This is sobering, but also oddly liberating. If we're not cosmically important, we're free to create our own meaning, our own purposes, our own values. The universe doesn't care, which means we can care however we choose. Our brief existence, however insignificant cosmically, is infinitely precious to us. That's enough. The role of imagination. Finally, our journey demonstrates the power of imagination in science. We've imagined something impossible, falling into a black hole, and through that imagination disciplined by physics, we've learned genuine truths. Thought experiments have a distinguished history in physics precisely because they let us explore situations we cannot create, visit places we cannot reach, test ideas before building expensive instruments. Einstein imagined riding light beams and discovered special relativity. Schrödinger imagined cats in boxes and revealed quantum measurements puzzles. We imagined falling into black holes and learned about horizons, singularities, information paradoxes, and the limits of physics. Imagination, far from being opposed to rigorous science, is essential to it. But imagination must be disciplined by mathematics and constrained by observation. Pure fantasy can imagine anything. Scientific imagination must respect what we know, extrapolate carefully from established principles, and ultimately submit to experimental test. Our thought experiment works because it's based on real physics, general relativity, quantum mechanics, not on fantasy or speculation. This balance between imagination and rigor, between creativity and discipline, defines good physics. We must imagine boldly to conceive new ideas, but we must test ruthlessly to separate truth from wishful thinking. Black holes inspire imagination. They're so strange they seem like fantasy, but they're real, observed, predicted by rigorous theory, and constrained by hard mathematics. The journeys end as we conclude this extended thought experiment, as we leave behind the black hole and the singularity and return to the everyday world of stable matter and flowing time. What should we take away? An appreciation for how strange the universe actually is, how much more there is than the narrow slice we experience directly. A recognition that physics can take us to these strange places, can reveal truths about reality that no amount of common sense would suggest. A sense of humility about the limits of knowledge, both practical and fundamental, and a recognition that some mysteries might remain forever beyond our reach. But also a sense of wonder and excitement. We live in an age where we can describe black holes, where we can predict what falling into one would entail, where mathematics and physics can take us to the edge of knowledge and show us what lies beyond. We can stand at the precipice of mystery and peer into the darkness, seeing further than any previous generation, even if we cannot see all the way down. The universe is vast, ancient, strange, and beautiful. Black holes are among its most exotic denizens, objects so extreme they challenge everything we think we know, so mysterious they've inspired decades of research and debate, so fascinating they capture imagination like few other cosmic phenomena. You have not fallen into a black hole, but by imagining it, by thinking carefully through what would happen, by following physics to the limits of knowledge and beyond, you've taken a journey that reveals truths about reality as profound as any actual journey could. You've experienced the universe at its most extreme, witnessed time and space behaving impossibly, and stood at the boundary where all our knowledge fails. The black hole waits, patient and eternal, hiding its secrets behind the event horizon. The singularity remains mystery, forever beyond our reach. The questions we've raised stay unanswered, waiting for future physicists to solve. But you've glimpsed the abyss. You've stood at the edge of forever. You've imagined the unimaginable and understood as much as anyone can what it would mean to fall into a black hole. And now, having completed this impossible journey, you can return to the familiar universe with new appreciation for its strangeness, new respect for the power of physics, a new wonder at the cosmos we inhabit, a universe stranger and more beautiful than we ever dared imagine, full of mysteries we may never fully solve but can forever strive to understand. The journey ends, the mystery remains, and the cosmos, indifferent but magnificent, continues its ancient dance, creating black holes and stars and galaxies, spinning out the grand drama of existence on scales from quantum to cosmological, inviting us to watch, to wonder, and to try our best to understand. The black hole has taught us well. Now we return to the light, carrying its dark lessons, forever changed by our glimpse into the abyss.